one by my face, right?
Well, we're live now.
We're live now. All
Sorry.
right. Welcome, Dr. Giesting. Oh, it's a pleasure to have you.
All right. Thanks, Jonathan. I appreciate you inviting me.
Yeah. Well, you've been a Wyoming native.
Wyoming resident.
Resident. That's the best we can do.
Yeah.
Yeah. You've been a foreigner in Wyoming, disguised as a Wyoming native for the last couple of years. So, and you were describing before the show a few of the ideas that you have for your research coming up next.
Sure.
Yeah. Any particularly strong inclination of what would you like to be doing a year from now?
Well, so what we were discussing before we started recording was the fact that my PhD is in uranium chemistry. And so I was discussing some of the weirdness that uranium and its neighboring elements in the periodic table have. What I would really, my long-term goal and what I hope to be where I hope to be in a year is somewhere that's, building toward this goal is really doing something where I can, marry like how solid materials are to some sort of, philosophical inquiry. I would like to be able to at least get to a point where maybe I cap my career with some of that.
Cap your career with a field of research that is describing physical things that we find in our world,
Yeah.
Combined with philosophical inquiry of like what caused them, what causality itself
are things.
Right?
So there's a whole Aristotelian question of, substances, right? So there is this difference between something merely having a form and something having a substantial form. And of course, that's hotly debated and has been for millennia, what exactly that means and whether we should care at all.
Right.
So we're pretty set on if it makes sense to talk about things being substances, then living beings are substances.
Mm-hmm.
And then what? Right. So some people believe that the right way to go about things is to say there's a tiling constraint and that everything in the universe is part of some substance or another. I'm far from convinced that's a great way to go, personally. But
can you unpack that a little bit? You said what constraint? A tiling constraint.
So you picture the metaphor is to picture like a bathroom floor. Every spot on the floor is covered by tile or grout, but we're going to ignore the grout, right? So every square millimeter of that floor is part of some tile,
right?
There are no exceptions. There are no gaps in this idealized picture.
Mm-hmm.
So there is no gap. There is no volume element of the universe that isn't part of a substance if the tiling constraint is correct.
Okay. And you at least quibble with that idea.
I'm not convinced it's the right way to go.
Okay.
Right? Do we consider intergalactic space with, what number of hydrogen atoms per cubic meter being a small number? Is that a substance? Should we just call it almost empty space-time?
Right.
Of course, Aristotle hates that idea, and I'm also not convinced by that. But Aristotle's a great mind of interesting ideas, but that doesn't mean he was right about everything.
Right. Still, if you explain space to a fifth grader, right, and then you ask them, okay, what's between us and the sun? If you had explained, they would say something like, well, nothing. Right. It's empty. There's nothing there.
Right.
And the tiling constraint proposes that, well, there's a little bit of something there, right? Random molecules, perhaps, but it is still part of something bigger.
Yeah.
Right. And you're saying, okay, that idea has merit, but you don't really want to fully endorse it.
Right. What is a substance? What makes it different? And what would qualify something as a substance? So this Robert Coons down at the University of Texas has an idea that he calls thermal substances. So everything that's not basically a living being would have to be part of a thermal substance. So it's unified by basically the laws of thermodynamics.
Okay.
Broadly speaking.
In layman's terms, that a little cube of tungsten on my desk has some interaction with a piece of tungsten that's buried beneath the earth 1,000 miles away.
Well, I mean, they would be separate substances, right?
Okay.
So,
But it has some interaction with that and with a piece of copper somewhere on Pluto.
if we had a piece of copper on Pluto, seems unlikely, but not impossible.
Hmm.
I mean, they would all be examples of the same type of substance. They would have the
Okay.
same substantial form,
Yep.
right? So there
Mhm.
would be, whatever hunk of metal and whatever asteroid, okay, so it's an iron nickel alloy. And then and then you come to the question of, well, at what point does, so I mean, that's where it becomes interesting to me as a geologist, since that's my background.
Yeah.
Minerals, so the question of how to define mineral substances, or I'm sorry, not mineral substances, mineral species is the term that we use.
Mineral species. Okay.
So that's a question that we've debated for a long time, and we have, somewhat decent answers hammered out.
Uh-huh.
Then there's the far more fraught question of how do you define a rock type?
Mm-hmm.
Because I mean, if you read the literature in the mid 20th century, it's just full of one-off names that somebody's invented to describe a rock that they found in, Trinidad. And then, somebody goes to Fiji and finds a rock that's almost similar, but hey, there's this other accessory mineral in it, so I'm going to call it something else. Okay. And so you get
And people were
insane.
kind of freelance at that point, right?
Yeah.
There was no one correcting them.
I mean, there were peer reviewers, who might raise some sort of argument, but they didn't have much ground to stand on, right? There wasn't much of a leg for them to stand on because you've got a definition. So finally, in the 80s, people came up with, for igneous rocks, they came up with a certain fairly crude system of like, okay, it seems like we have a visitor.
Fine. Sorry. 5 volcanoes?
That's one kind.
That's one kind. Okay.
Extrusive igneous rock.
Uh-huh.
There's also intrusive rock.
Uh-huh.
So if you go up in the winds, right?
Mhm.
So once you go past a certain distance into Sinks Canyon, you run into the Louis Lake batholith.
Mm-hmm.
So a batholith is just a giant, probably contiguous set of igneous plutons. I mean, the idea that they're like the Sierra Nevada batholith, if it was one batholith, would have been, I don't know how many 100 miles long.
Uh-huh.
They were probably individual intrusions that just look so similar they can't be told apart
Okay.
readily. But yeah, so that would be intrusive rock. So magma that just never makes it to the surface, but cools off somewhere close to the surface.
Okay. Okay. And when we say intrusive, it means that it got forced up from farther down in a magmic form and then cooled.
Yeah. Magma comes from a Greek word that literally means something like paste.
Okay.
So
Pasty rock.
Yeah. I mean,
Yeah.
it is seldom completely melted. There's usually a few crystals in it.
Mhm.
If a magma is completely melted and is above the temperature called the liquidus at which it became completely melted, then it has what's called superheat.
Mm-hmm.
And there's not much. The main way to get superheat is if you have a magma that melted at depth, which means that it was near it, below its liquidus,
Mm-hmm.
and then was lifted very quickly, and you
Very
release the
quickly
pressure.
before it had time to.
Yeah, you release the
cool
pressure
down.
on it, then its liquidus temperature goes down, and so it can have superheat for a certain length of time before it cools back down to ambient.
Okay. So what does the term igneous refer to?
I mean, it means fiery.
It
just
means
means
fiery.
the hot rock.
Okay.
It literally means a rock that was melted.
Okay.
Right. I mean, it etymologically means fiery rock.
Fiery rock.
But
Okay. So we
it
think
means
volcanoes, but
geologically.
it's
Yeah.
really any rock that was magma.
And,
at
and
one
volcanoes have intrusions underneath them.
Mm-hmm.
There's a certain amount of magma that never made it to the surface to become lava.
Right. Right.
So if you go to where I was just on Monday down to the Boar's Tooth, if you've been down there in the Red Desert,
Mm-hmm.
you go up to that thing and you see this conglomerate that the magma just kind of chewed up some of the neighboring sedimentary rock and has just, I mean, it's like almost, I hate to say it, but it's kind of like a pile of garbage. And you go to the interior, like
Crash rock.
shaft,
Yeah.
and then that's just the cooled magma that never made it out of the volcano.
Mm-hmm.
So presumably, however many tens of thousands of years ago, that plain around the Boar's Tooth was, covered with lava flows from the Boar's Tooth, but that's all eroded away.
Mm-hmm.
It's gone somewhere else.
Okay.
So there's a combination of of extrusive and intrusive rock there.
Okay. So intrusive, to me, it sounds as if super hot rock, right, is being forced surface towards the surface.
Right.
Extrusive rock would be
It's forced toward the surface and makes it all the way there and actually comes out.
okay. Okay. So it's a pimple that pops.
There you go.
Yeah.
Yeah.
Paul's like, who the hell is on the other side of this mic? You know?
I don't know that metaphor that occurred to me in exactly that context before, but it is reasonably apt. Yeah. Yeah. There's an eruption. You can use an eruption in either case.
Right. Okay. Yeah. All right. All right. I'll try to keep my language more dignified for the rest of the cast.
It's okay. Just have some more whiskey. Just have some more of that.
Oh, it'll get worse
Yeah.
if I have more whiskey. Yeah.
Okay.
What is the batholith that you're referring to? You said the Louis Lake batholith.
The Louis Lake batholith. Yeah. If you go see that pink granitoid, granite-like is all that means. It's not exactly a granite. There's a specific definition in this, scheme that I'm describing for granite sensu strictu, which definitely does not include the black rock that my dad bought, was sold by I don't know what shyster. I mean, it's a trade term, black granite.
Yeah.
And it's one of the things that just leaves me as a geologist, like, face palming, because it's by definition can't be granite if it's black. It has the wrong minerals in it to be granite.
Right.
So
Right.
But whatever.
Yeah, you won't even cook on those countertops. You're like, forget this. Yeah,
I mean, I would just call it a trap rock or something like that.
I just don't think that has the sex appeal that people need when they're selling
in
it.
a world with Fetty Wap. I mean, trap rock has got a certain.
You can sell trap rock, yeah.
Certain markets anyway. Black is beautiful, right? So, gosh, did I say that out loud? Of course I did. But that's all right. So. Anyway, but so you go up there and batholith just means deep stone. So it's just something it crystallized at depth. The intrusions that make it closer to the surface have more defined shapes usually, but a batholith is just kind of a big amorphous mass. It's usually somewhat sausage-like, but it goes on for miles. You wouldn't call it a batholith if it was below a certain number of square miles an outcrop.
Okay.
So,
but sausage shaped in the sense that they tend to be extremely long.
Yeah,
well, relatively narrow.
I mean, they're longer than they are broad. Yeah, they usually have an extended direction, especially if you think of something like the Sierra Nevada batholith. It's along the core of the mountain range.
Okay. And that's because on a grand scale, it's almost like a sausage being squeezed out of a die, right? Where it's being pushed from a narrow aperture.
Being pushed up from below. So it's really being pushed from one of the sides of the sausage.
Okay.
Yep. I mean, I'm probably I am overstating the degree to which they are that shape. The Louis Lake batholith is probably actually kind of blocky.
Yeah.
Sierra Nevada batholith is kind of the one that occurs to my mind as an American geologist, and that is fairly long. And there are others at the core of mountain ranges that are like that.
Right.
Of course, and then and that one really is because of plate tectonics. So plate tectonics does things along lines, along plate boundaries.
Yeah. Okay.
So at one time, the Sierra Nevadas were, above a subduction zone, back when California had a subduction zone instead of a big long transform fault.
Jeez, man, you're throwing vocabulary at me faster than I can keep up.
Everything's connected to everything.
Yeah.
So you've heard of the San Andreas fault,
of course.
And so transverse fault just means it's slides past sideways, as opposed to up or down.
Okay, up or down. Okay, and what's the up or down referred to?
If you look at the surface where the two, a fault is just a break in the earth.
Yep.
And if there's motion along it, well, if it's just a break in the earth, you'd call it a joint.
Okay.
If there's motion along it, you call it a fault. And it's usually slanted. So if you can picture, dear listener, a slanted, plane within the earth. One side's going to be on top and one side's going to be on the bottom.
Yep.
And so if the top side slides over the bottom, you have what's called a reverse fault. And if the top slide slides back and makes way for the bottom, you have a normal fault. And if they just slide past each other sideways, then you have a transverse or transverse fault.
Okay.
Yeah.
All right.
So, and the San Andreas is just an enormously long, unusually long transform fault.
Transverse, transform.
You can call it either one.
Okay. Gotcha.
The name
That's where
is
we're getting the
simply-
earthquakes, right? Is
Yeah.
because these two things catch on each other and then release.
That's right,
Catch,
yeah.
release, right?
Yeah.
Okay.
Yeah.
And then you were saying the two other types of motion are when you basically almost like two plates, stacking,
Mhm.
right? One is definitely on top, the other is underneath.
Yeah.
And sometimes the top one rises and sometimes it slides back.
Yeah. So if you
so to
have,
speak.
and if you have somewhere where the earth is being stretched,
Uh-huh.
you get normal faults because the
Okay.
earth is kind of pulling apart. And that's when you would get that motion where the
Hmm.
upper plate slides off the lower one
Okay.
because they're being pulled apart. If
Yeah.
you have places where the earth is under compression, you get a reverse fault.
Mm-hmm.
And an extreme form of reverse fault would be a thrust fault,
Mm-hmm.
which is what many mountain ranges, including the winds, were built by.
A thrust fault. Okay. Just two, it's a car crash in slow motion. It's
Yeah.
just two massive objects pushing into each other.
Yeah, and one
Okay.
and one goes up and one slides down,
Okay.
and they.
And is that
slide.
why the winds, I mean, especially here in the foothills, like, the butte, right? Everything is slanted,
Yes,
right? Like
absolutely.
all the foothills, like you look at it and you're like, man, it looks, everything's tilted.
There's this
the same
incredibly-
way.
Yeah, incredibly consistent dip. It's called.
Hmm.
I mean, there's a technical term for you, dip.
Mhm.
But yeah, so the winds strike, the complementary term. They strike northwest
Mhm.
and they dip northeast.
Uh-huh.
And it's a consistent, 6-7 degrees for just miles and miles and miles.
Uh-huh.
Which is why it's a great geology laboratory.
Mhm.
That's why my first visit here was in 2000 to go to field camp
Mm-hmm.
with the University of Missouri's field camp up in the canyon.
Sure.
So
Sure.
because it's just a great playground for that.
Do these different spots all have their signature angle, or do we find a similar angle all over the globe?
Well, there would be different angles, and in fact, for the winds to be so consistent as they are is somewhat unusual.
Oh, really?
Most of the time, if you go to a mountain range, the dip will change from one spot to another.
Okay.
I mean, and it changes in the winds too. It just doesn't change as fast.
Okay.
So it's unusual how consistent it is.
Okay. Okay. So there's not like the signature angle that we find in,
No.
in rift after rift after rift. Right.
No.
I remember.
Yeah.
Go ahead. Go ahead.
Yeah, I don't even think the thrust fault underneath the mountains, which is at a much steeper angle. Even that, I don't believe there is a magic, most thrust faults are 35 degrees, like the winds or something like that.
Right. I remember Dr. Bolin telling me that rivers have this magic ratio of the distance from their headwaters to their mouth at an ocean versus the mileage that they actually transverse as they snake down across a continent,
Sure.
right? And he said that ratio was very, very, very close to pi. And I was like, whoa, that's really something. But yeah. Yeah. But no similar relationship found in the geology you're describing.
Not so much.
Okay.
Yeah. I mean, there's certain tendencies in rock mechanics for things to break at certain angles, but those are like homogeneous blocks of stone, and that's exactly not what the Earth's crust is. The Earth's crust has a history.
Uh-huh.
It's been through trauma.
It's been through, right. Pimples, the acne, that's the least of the problems, right? It's had bones broken.
That's right.
Yeah.
Yeah, exactly.
The Grand Tetons, have ever since I was in college, have always struck me as remarkable in that you've got the Antelope Flats. I mean, that's literally what they're called.
Yeah.
And then the Tetons. I mean, just right. Okay. So what's the geology that's going on there?
So that's contemporary and is much more mysterious.
Okay.
Western North America has this weird trait, shall we say, that its older geology is easier to explain than its current geology.
Oh, geez.
Its
Okay.
older geology is like, oh yeah, okay, there are mountain ranges. They were built over subduction zones, and there was collision and folding and all this sort of everything. Like the Himalaya. It looked like the Himalayas, or it looked like Japan, or it looked like the Andes, and it all fits together reasonably well. I mean, geology is never. It's a messy science. That's in some way it's abstraction.
Okay.
But
as in there's multiple explanations for the same thing, or just all explanations are somewhat gappy?
Yeah, they all have gaps.
Okay.
I mean, and then there are sometimes conflicts and overlaps as well.
Okay.
Yeah. But broadly speaking, North America 100 million years ago, it looks like we have a reasonable handle on why it was doing what it was doing.
Okay.
why the severe orogeny happened west of here, why the Laramide orogeny, which includes the winds, happened.
Uh-huh.
All of that makes a certain amount of sense to us. And then we get to the last 20 or 30 million years, and the subduction zone off California shuts down, and mountains stop being built in the ordinary way. And then the basin range just starts lifting for some reason. And
Wait, did you say nifting?
lifting.
Oh, lifting. Okay, I was like,
It's
man, are
rising.
we doing geology or is this like a surfer term? You know?
Oh, yeah.
It's a total bummer, you know?
Yeah.
Yeah, the plate started nifting and it crashed. Yeah.
That's a climber term, right? Yeah. So there are a lot of climber terms that have proper geological equivalents, but the climber terms are more fun.
Right.
I should get a little closer to the mic too, shouldn't I?
Yeah, how
I've been
are our
moving
audio's
back and
doing
forth.
okay?
Yeah.
Yeah.
It's been doing great.
I think you're doing
You guys actually have a mixer board. You guys are so pro.
Yeah.
Golly. But yeah, but for some reason, the West, like, the Intermountain West is the locus of this unexplained uplift. Why is it that when you go from the Mississippi River to Denver, you're just going up and up and up and up? I mean, it's geology, so there's hills and valleys and whatnot, but it's pretty dead blame consistent. And it goes up a mile in that, however many 100 miles that is.
Right.
And that's very odd. And then, so the winds stopped being built in the conventional sense tens of millions of years ago. They should have worn down by now. In fact, they probably did wear down, and now they've been pushed up another 5 or 7 or 8,000 feet for no reason.
No reason that we can pin down.
Right.
Yeah.
Exactly. Not for no reason, but it's not clear why.
Okay.
So
the winds should be stubbier than they are.
Is it related to the mega volcano in Yellowstone? Or no.
You'd
What's that
think
called? The
that
caldera?
have something to do with it, but that's where the mysteries, when people try to make that more specific, they keep running into roadblocks. Like, actually, you'll come up with an explanation. It sounds plausible, and then it's like, not really, not quite. Yeah, there's a whole bunch of stuff, so, it seems like the Yellowstone volcano attaches to a track that goes all the way across the Snake River plain. So, I mean, if you look at a relief map, like one that literally is bulged up where mountains are, you see, and you look at Idaho where the Snake River flows, there's just this crescent shaped hole. Like there's just this trench through the mountains. Why? Well, it seems to have something to do with the fact that, the Yellowstone volcano seems to have been moved across that track and blown it out. That's probably an oversimplification, but that seems to be part of it, because you can follow that track and you can follow volcanic activity back, several million years. And it seems to end back in, eastern Oregon and Washington state, where there is an ocean of basalt that was just flooded over the landscape. It's literally called a flood basalt, the Columbia River basalts. And it seems like that ought to be connected. And yet, once again, when you push on it, you find inconsistencies. That the dawn of plate tectonics in the 1960s was one of these periods when you had big idea people. So Galileo was a big idea guy. He wasn't right about everything. He was right about enough things that we now adulate him as a great, amazing scientist. But the history of science is kind of littered with carcasses of people who had big ideas like Galileo and were just kind of wrong about nearly all of them.
Okay, so they're kind of like tech entrepreneurs, right? We know about Musk and Zuckerberg and Gates because their ideas worked, but there's for every one of them, there's a dozen tech entrepreneurs who try to let's do this. Like what was it, Healthion? Let's take healthcare out of the sectors that it's in and put it in a more privatized and more digital space, and it just didn't work, right? Who knows the name of the guy who started Healthion? Well, like tech historians do, but right.
Yeah, exactly.
And you're saying science is similar in that a lot of people have said, well, maybe everything we've known up till now isn't true, let's try this. And a lot of those people were wrong.
Yeah, or what I'm thinking of here is more like there's this big empty gap in our explanations. Maybe this could fill it.
Mm-hmm.
You know, so I'm thinking of now as a guy named Jason Morgan, who is a big name from the dawn of plate tectonics in the 60s.
Mm-hmm.
And Morgan had this idea of what's called a hotspot as a mantle plume. And, you know, if we may as well go big or go home and say, you know what? So there's this upwelling of hot material somehow making it through the, as my master's thesis advisor likes to mention, solid mantle that is solid. Maybe it flows to some extent, but it is solid. But somehow this hotspot can just come up through the solid mantle and make its all the way up to the Earth's, you know, tectonic plates at the surface and create anomalous volcanism. Because plate tectonics, if you want to put a round number on it, explains like 90% of what happens on the Earth's surface.
Mhm.
And then there's Hawaii.
Hmm.
And then there's Iceland. And then there's Yellowstone.
Mm.
And a few things like that
Okay.
that need some other point source for volcanism.
Hmm.
Because
Mhm.
there it is. I mean, like Hawaii, it's just too clear to be, you know, believed. Here is this volcano. Here's the active volcano at the end of this line of islands that becomes seamounts that track all the way to Kamchatka.
Hmm.
And it's just this one long chain. And the further northwest you get on the chain, the older the thing is. It's just too clear for words that there's something burning a hole in the Pacific Ocean crust,
Hmm.
and the Pacific Ocean plate has been dragged across it. Now, maybe that thing it's a little heterodox to say maybe that plume is moving.
Mm-hmm.
It almost has to be because there's this kind of inexplicable bend that used to be like, oh, that tells us the Pacific Ocean plate probably just, you know, took a 30-degree turn in the direction it was moving. Why?
Yeah.
That's yet another one of those things where it's like, the closer you look at it, the worse that explanation looks.
Mm.
So it's easier if the plume is moving,
Okay.
and the plume, it's probably easier to get this point source to start moving north or south as compared to getting the plate to, like, you know, suddenly change direction by 30 degrees.
Hmm.
I mean, I
And
suppose
you say plume. I mean, and again, this is magmous rock
picture-
that's
yeah.
like erupting
Picture
from beneath the crust.
solid but hot, you know, somewhere close to its melting point, so it will flow ish. And it is hot, so it is lighter than its surroundings. So for some reason, there's a disturbance of the core mantle boundary
Mm-hmm.
where you can put anything down at the core mantle boundary because who's ever going to test it? I mean, you can do seismic studies and try to get at that.
Mm.
But that's black magic.
Okay.
That's just about black magic.
Okay. These are fiction writers posing as scientists.
I read a text that was quoting an earlier seismology text
Mm.
or paper, I think, well, where the guy was dryly commenting how, you know, minerals undergo phase transformations when you squeeze on them. So you take the minerals that are at Earth's surface and you put them 100 miles down, they change into other minerals because at the Earth's surface, there's very low pressure. And so the atoms are free to arrange themselves into a light, open framework that satisfies their bonding requirements better. But once you've subjected them to that much pressure, they're going to respond. And so they're going to get denser and they're going to cram themselves into different configurations. And once you start doing that, once you pass a certain tipping point, they're going to change structure completely. So the guy was using that as a metaphor for language also undergoes phase changes when you subject it to the pressures of the Earth's core. What on the surface we would call an uncertain mixture of all the chemical elements becomes at the Earth's core solid iron. And, you know, and other things like that, where we pretend a certainty that we don't have. I mean, that's a human failing. That's why science is so hard. I mean, so
Yeah, and it applies to a lot of other fields besides geology, right?
yes. Oh, absolutely.
Yeah.
I mean, you can, you know, to another geological example, just that's a fun one. So you've heard of Martian meteorites.
Couldn't tell you a thing about them.
Okay.
Yeah.
Well, I mean, that's, you know, that we have chunks of Mars. They have fallen to Earth as meteorites.
Mm-hmm.
And they've made a certain Bedouins a certain
Right.
amount of.
Why are we trying to get to Mars? Mars is coming to us. Yeah.
in really traumatized little chunks.
Yeah. Yeah.
And really traumatized little chunks.
Hmm.
Because what has to happen is an asteroid has to crash into Mars and send bits of Mars flying, and then those somehow have to cross Earth's orbit enough times to actually fall to Earth,
Hmm.
which is not the easiest thing in the world. But we
Okay.
we are to the point where we have over 100 chunks that we're pretty sure are from Mars.
Okay.
Wow.
So the state of the art when I was born in 1979, let me hitch up my adult diapers here,
All right.
was that we had meteorites, and most meteorites are what are called, well, I mean, there are iron meteorites and there's stony irons, and then there's a lot of rocky ones. And most of the rocky ones are called chondrites, which are made of little balls that condensed out of the original solar nebula, broadly speaking.
Hmm.
Then they got packed into an asteroid and then broken back apart, is usually their history, is definitely their history. But that's what most of them are. So they do not look like Earth rocks.
Hmm.
There are a few weird, really psycho Earth rocks that maybe look a little bit like chondrites.
Hmm.
But for the most part, chondrites are like, ooh, ew, that's weird. That might be a meteorite. But once in a while, you'll find something. You'll either see it fall, like happened at the village of Chassigny in France, and whatever it was, 1815 or something like that.
Mm.
And you go pick it up. It's like, wait a minute, that looks like an Earth rock, but it's got a fusion crust that fell from the sky.
Hmm.
But it looks like an Earth rock, but it fell from the sky. So those are called achondrites, not chondrites.
Hmm.
So in
They're earthier than
1979,
they should be.
do what?
They're earthier
They
than
look
they should
more
be.
like a rock from the planet Earth. Yes.
Mhm.
So they have been further processed because the Earth presumably condensed from chondrules originally, and then it, melted and stuff,
Mm.
and then has done a whole bunch of other geology to itself since then.
Mm.
And so you have rocks that have histories.
Mm-hmm.
Yeah.
They're igneous rocks and sedimentary rocks and metamorphic rocks, and none of them look like chondrites.
All right.
So these look like mostly igneous rocks of various kinds, in
Okay.
fact, almost entirely.
Hmm.
And so people had gathered them and, had different families of them that had certain physical and chemical similarities.
Yep.
And then we sent we sent a lander to Mars with a mass spectrometer to measure its atmosphere.
Hmm.
And then somebody said, oh, wow, that's an interesting signature. There's, these certain noble gases in this pattern that's very unlike Earth's atmosphere. And then somebody said, wait. That means that we could tell, because we've been kicking around this idea for a while that some of these might come from Mars. Mars is further away from the sun. If something got kicked off of Mars, it would fall toward Earth, right?
Mm.
But I mean, how could we tell? But now we could tell.
Mm.
So if you took a pristine one of these, found a pristine surface and had some very sensitive lab equipment, which in the early 80s we did have, you heat it up, you see what gases are given off. And certain of these achondrites had a signature that was like, that's Mars's atmosphere.
Mm.
That's Mars's atmosphere. That's not Earth.
Hmm.
So, and from that point on, we're like, oh, we have chunks of Mars. Isn't that handy? So, why did I go on that long?
Wait, and then
I'm
wait,
almost
hold,
getting there. But
yeah, and these chondrites. So these chondrites, when you cook them, they look they continue to look earthy, right? So these are
so you have a chondrite, and chondrites themselves come in all different scales of having been cooked.
Mm-hmm.
Some of them have been heated significantly,
Mm-hmm.
and so the minerals in them, the least cooked ones are called carbonaceous chondrites
Uh-huh.
because they have volatile carbon bearing stuff in them.
Okay. As in it'll burn more.
You could set some of them on fire, I
Okay.
suppose. I've never heard of anyone trying that experiment, but anything for science, right? But there are some of them like enstatite chondrites that are, they've been heated to fairly high temperatures. They just haven't been melted.
Okay. But we're convinced the scientific community is convinced that these are chunks of Earth that have gone up into the atmosphere and then come back. Am I tracking you correctly?
No one believes that.
No one believes that.
No
Okay,
one's believed that since like the 18th century.
Okay. So
that'd be a little too much to say, but sometime in the 19th century.
Okay, so even though they look earthy, they're not
the achondrites.
The
achondrites look earthy.
Okay.
But they are not. They're from other large bodies in the solar system, like Mars.
Okay.
Or there are the very largest asteroids in the asteroid belt got big enough to have igneous activity.
Mm-hmm.
So there are 3 different classes. The Howardites, Eucrites, and Diogenites all come from the asteroid Vesta.
Mm-hmm.
And we now have like a probe that's actually, it didn't quite orbit Vesta. Well, maybe it did. I can't remember the details of that mission. It was a crazy mission. It visited more than one asteroid, which is actually pretty hard to do.
Yeah.
But yeah, so it studied Vesta very closely, and we are now basically convinced that yes, the HEDs did come from Vesta because Vesta has been hit by something large relatively recently and sprayed pieces of itself out into interplanetary space. And we've collected, I don't know how many dozen of those.
Okay. So is it true to say that despite any similarities to stuff we find on Earth, both the achondrites and the chondrites, no one thinks they actually came from Earth? It's just that some of them look earthy and some of them don't.
Right.
Is that true to say?
Yeah.
Okay.
Yeah.
Gotcha. But we are convinced that some of them definitely came from Mars.
Yes.
Okay.
Yeah. A lot came from the moon, believe it or not. The moon's very close. It'd be pretty easy to hit the moon and then have pieces fall on us.
Yeah.
Sure.
Although I don't think we found or verified that we had any of those until after the Apollo missions. And it's like now we have this is from the moon, kids. Hey, it looks like this thing over in my museum. It probably is from the moon too.
Yeah.
You know, easy to believe.
Yeah.
Getting more of those.
Yeah.
Yeah.
Right. All of a
But,
sudden, my moon rocks got damn boring.
Right.
You know, now we can just send people to go get them. You know.
Right. Yeah, exactly. Yeah. That's so easy to do. We haven't done it since 1970. What now? But yeah. Yeah, I saw a guy, he came to the University of Tennessee when I was working there, who was the one geologist we sent to the moon, and I forget his name right now. I'm spacing on it, but he was on the very last Apollo mission. And yeah, he was kind of irate that we haven't sent anybody back to the moon. And well,
50 years.
yeah, at that time was only 40,
40,
but yeah.
I know. Why don't we send more people? Why did NASA get so boring?
Yeah, that's a good question. I mean, so we achieved that. The next thing is like sending people to either Mercury, not Mercury. Mercury is another few steps. Is sending people to either Venus or Mars. Venus is kind of, well, do you want to like float in something, 60 kilometers up in the atmosphere? Because that's what's safe. You ain't going to the surface. I mean, the Soviets sent, I don't know, a dozen and a half probes to crash into Venus's surface. That was kind of hysterical. I mean, I think the longest one, did it last an hour on the surface?
Wow.
Sent a few photographs back and some really, really crude chemical analyses that might be basalt.
Don't know.
That'd be pretty hard to say for sure. I mean, probably Venus is covered with basalt. Venus from radar, which can get through the clouds. We Americans sent a probe to orbit it and map it with radar, which is still kind of the state of the art for Venus science, is the Magellan probe from the early 90s. It looks like it's covered with lava flows and volcanic, vents for the most part. You need like actual proof, right?
Yeah.
So just the fact that it looks like it could be basalt, you'd like, and it probably almost certainly has some sort of different details than Earth. You'd like to get some of that, but that would be very hard. Or so I mean, to come back to NASA, we send somebody to the moon. The next step is another planet. That's another 2 orders of magnitude harder, probably. So we're bored with that. We don't want to do that just now. And then, I mean, again, this is the era that I lived through, is the Reagan administration, when, as much respect as I have for Ronald Reagan, I mean, he did kind of make the deal with Satan, like, okay, we'll just spend on everything. We'll spend on defense and on domestic spending. And the whole, the era of the $400 billion, budget deficit was born, that we kind of walked back from in the 90s. And then Gulf War II came, and it's just been open throttle since then. So, spending that chunk of the national, gross domestic product on, the next cool thing, it's just never gotten back on anybody's radar.
Do you think there's a pretty high chance that Musk will get someone to Mars?
I don't know what to think of Elon Musk. I mean, I don't know. I mean, I always have this worry in the back of my mind that Elon Musk is like posing as this great, capitalistic, amazing entrepreneur, and he makes all of his money one way or another through, government chicanery. I worry about that. I worry a lot. Did I mention I come from rural Indiana? Yeah. That sort of comes with the territory. But
A
yeah,
long line of laying awake at night, being like, "Oh no,
right.
what if?
I mean,
What if the conspiracy theorists are right?
that
What if the bullet really did curve? Yeah. What if the CIA really was down there?
right?
Yeah.
Right. Yeah. Yeah. I mean, that's probably not what my mother and grandmother were laying awake worrying about, but you know, they did do that sometimes.
Yeah.
Yeah, I mean, I just don't know. Um, I think that I'm certain I'm being too pessimistic about him. I'm certain that he's accomplished something. He's accomplished a lot of things. Tesla has gotten a lot of engineering done. SpaceX has gotten a lot of engineering done. But I mean, where SpaceX is at now and what it would take to get people to freaking Mars, I think there's still a pretty big gap there.
Gotcha.
I would not want to go to Vegas and put money on him making it in the next 10 years or something for sure. Or even 20.
Wow.
Okay. So you don't see it happening in his lifetime. Right.
Very
Because he's in
no,
he's what?
because he's gonna
50s, early 50s.
he's gonna stress himself into the grave by 20 years from now.
Okay.
Yeah.
So true. He's
That's probably what I would go
he's
to
an
Vegas to put money on.
Indianian at heart. Yeah.
Something like that.
Yeah. He's lying awake at night, being
Yeah.
like, "Why if we don't make it to Mars?" You know.
Yeah.
Right.
Right. What if I die before my vision is achieved?
Right.
Can you comment on the EV debate in a way that could shed some light on it for us laymen?
The EV, the electric vehicle.
Yeah, I mean, I hear it both ways, where it's like, we're getting away from fossil fuels, and that's a very healthy thing for our planet. But then I also hear like, the resources it takes to extract enough material to make the batteries that EVs require,
Right.
actually, and then the translates to a heavy battery pack, which translates to a heavier car, which means it takes more braking to stop a car, which means that your brake pads actually wear down faster,
Yeah.
which means you're releasing more brake dust into the atmosphere. People are saying, no, actually, EVs are worse. I'm like, is this politically motivated? What's going on here?
That sounds like a little bit of a Rube Goldberg machine as far as a criticism of EVs.
Mhm.
It sounds a little convoluted.
Mm.
I mean, so the concern about batteries is real. I mean, so the state of the art right now is a lithium battery.
Mm-hmm.
Lithium is a rare element.
Mm-hmm.
The universe doesn't like making lithium for various nuclear physics reasons.
Okay.
So there are people working.
It's like a delicate souffle. Like all the conditions have to be right.
That's a good way to put it. Yeah.
Okay.
Yeah, actually.
Okay.
I mean, so the models, I mean, and I emphasize models, say that at the Big Bang, the universe created an awful lot of hydrogen, a little bit of helium, and a microscopic amount of lithium.
Uh-huh.
And then stars, make all the heavier elements, but stars don't like making lithium for various, again, nuclear physics reasons. So I guess there's a little bit that comes out of stars, but there's just not a lot. And so in the battery literature, which I've read to some extent and actually have even tried to get involved with some of that work myself in the past.
Okay.
Is a bit of a stretch from what I've done so far, but there are people working on sodium batteries.
Okay.
Now, sodium is, of course, there's tons of it.
The oceans are full of it.
The oceans are full of it. Not
Okay.
as full of it as they are of hydrogen, which if we ever got fusion off, the ground, then we have a lot of fuel. It's like Doc Brown at the end of the first Back to the Future movie, like, I need fuel. And he just goes to the garbage and starts throwing things into Mr. Fusion, right?
Right.
That would be a beautiful world if we could get there.
If we could burn our own garbage, yeah.
Yeah, exactly. But that's still some time out. Gosh, and that's, of course, we've been working on that problem for however many decades. I mean, since the 60s, right? For
The fusion problem. Okay. What about the sodium battery?
Sodium batteries? Well, I mean, so the obvious problem there is that sodium is heavier than lithium. And there are other subtler problems.
Okay.
I suppose. Otherwise, for certain applications where weight doesn't matter that much, if you have a storage battery in a fixed location, why would you ever use lithium if sodium would work?
Hmm.
Right.
What about shipping, right? I mean, does a
I mean,
cargo ship
ship it,
really
just ship
care?
it once and then it's done, right?
Oh, sorry. If you were powering something that was
Yeah, if you-
waterborne.
If you had something, yeah, I would say, yeah, shipping would be another where you care about weight, but not that much.
Okay.
Not nearly as much as you do for a car.
Mm-hmm.
Not nearly as much as you do for a land or air vehicle.
Mm-hmm.
Those are more demanding applications
Okay.
for weight.
Uh-huh.
So, yeah. So I'm not really sure. Man, of course, it sounds like a great idea on the surface, and then you scratch the surface, you find the difficult details. I mean, yeah,
That's life.
it's life,
Yeah.
isn't it? Yeah. It
Yeah.
sounds great. Sounds great as an idea. So yeah, so lithium is a bottleneck. Lithium is a big bottleneck.
Because there's just not that much of
There's
it.
just not that much of it.
Okay.
Now, fortunately, that's not the only part. The reason that we have as much of a lithium economy as we already have
Mm-hmm.
is the fact that despite the fact that there isn't much lithium, it separates itself out easily.
Okay.
So there's different elements have different geochemical affinities.
Mm-hmm.
Like, so there is a minuscule amount of uranium. In
Mhm.
fact, there's a lot less uranium than there is thorium in Earth's crust. But the thing about it is, because, as we mentioned before we started recording, uranium is the lunatic fringe of the periodic table.
Mm-hmm.
It does stuff that nothing else does, uranium and its neighbors, and uranium is the only naturally occurring one of its neighbors.
Mm-hmm.
So it will draw two oxygen ions up real close to it to make this complex cation, which nothing else does,
Mm-hmm.
and will make all of the oxidized, when uranium's in contact with the atmosphere, it turns yellow, forms this complex cation, and its own suite of minerals that nothing else participates in the uranium site. I mean, other things do participate in it, but
Mhm.
you will get these uranium minerals, and uranium is going to go somewhere. So it's going to be in a uranium mineral. So they
Okay.
will segregate itself out and make itself essentially easy to mine.
As in it's relatively stable, right? It's not
Well, it's not widely
decaying itself.
Yeah, I mean, uranium is a very long. The two isotopes of uranium are 235 and 238, and 235 is the short one, and that's hundreds of millions of years half-life.
Half-life. Okay.
Yeah.
Gotcha.
238 has a half-life measured in billions of years.
Okay. All right. So
Yeah, sometimes.
yeah, right. We don't have to worry about it evaporating while we're on our lunch break.
That's different than like protactinium or astatine or something like that.
Mm-hmm.
Those you do have to worry about. Oh, you go back from your lunch break. I think you have to go back to the atom smasher and make some more of them because there's not going to be much left. But yeah. But what I'm talking
Go through the drive-through, all right?
what I'm talking about is extracting them. So
Okay.
for example, gallium, the mineral or the element gallium, I should say, is directly below aluminum on the periodic table. It
Mhm.
acts basically just like aluminum,
Mm-hmm.
and there's a lot more of it, I'm pretty sure, than there is uranium.
Mm-hmm.
But it's just everywhere it's just everywhere aluminum is, and aluminum's a major element.
Uh-huh.
So there's just, however many 100 parts per million of, gallium tagging around. Go mine that. That's awful. That's an awful situation because I have to separate it from an element that's very much like itself, present in much higher concentrations. I bet there would be a ton of economic uses for gallium if we could get it reasonably cheaply.
If you could draw it off from the aluminum.
Yeah, if we
Okay.
could get gallium at the same price as like lead, which I'm almost certain is less common, like in terms of its crustal abundance,
Uh-huh.
we'd have probably all sorts of uses for it.
Okay.
But it's too expensive.
Okay.
It's too expensive to extract.
Again, forgive me for turning everything into an analogy, but I mean, I'm thinking of like when I work cattle, like, the calf wants to stick with its mom, right? Or,
Right.
the cows generally want to stick together. You're saying in an analogous way, you want to extract the gallium from the aluminum.
That's right.
You gotta really put a lot of energy and effort into drawing it off.
That's right.
And it doesn't want to be.
Energy,
Right.
effort, time. Yeah.
Right.
Yeah.
Right.
Yeah,
And if you could, yeah, super useful. But the energy and effort that it takes to draw off.
Gallium is a bizarre metal. It melts in your hand.
Mm-hmm.
It is solid at quote unquote room temperature,
Mm-hmm.
but at human body temperature, it melts.
Okay.
Wow.
So So you could use it in a ton of applications where you use mercury. It would be
Mhm.
far less toxic.
Okay.
Mercury is mercury. Um, they've ratcheted, the EPA has ratcheted the closure levels for mercury down to like obscenely small numbers.
Right.
Just because you know,
Basically, if we
it's
can
just
if we
bad.
can find it, it's bad for you,
That's
right?
right.
Like,
Yeah.
yeah.
Yeah, that's it. That's right. Yeah.
Mhm.
The detection limits are basically the closure limits. If we
Mhm.
can detect it, it's bad.
Yeah.
Um, yeah. So, but whereas lithium and uranium are more loners,
Uh-huh.
right? Gosh, we've opened so many plot threads here. I don't think I could ever close them.
You'll just have to
Yeah.
come back.
Right?
Yeah.
Yeah.
Exactly.
Yeah.
Um,
Well, you're
yeah.
doing, I mean, you're doing a fantastic job of making this accessible to people who don't have a background in chemistry, which is
Yeah.
impressive. Yeah.
I've learned so much.
Yeah, yeah, exactly.
Most of
We need one guy just writing down all the terms, you know, nifting, you know.
That's right. That's right. It's just being nifted for some reason.
Yeah.
Yeah. There we go. Okay.
Yeah. But let me use that segue. I mean, so forgive me for being sensationalist, but I'm going to indulge myself for the sake
Sure.
of our audience. But one of the first conversations you and I had about 4 years ago
Sure.
was about the Yellowstone caldera.
Oh, sure.
Right. And I was kind of picking your brain of like, okay, what's hype? What do we actually know? What are the odds that it blows up in our lifetime or our grandchildren's lifetime?
Right.
What would that look like? And you had some really interesting thoughts to share on that.
Oh gosh. Okay.
Yeah.
I mean, so the stats on it, and now I'm trying to remember. I'm pretty sure we talked about this after we started recording. So you remember the Snake River Plain, right?
Yeah.
So the thing about it is that, in basically its current location, Yellowstone has already gone off 3 times.
Okay.
Oh.
So now, I mean, so the really, the bureaucratic mindset. So there's a line from the end of Star Trek 4. If you've never seen Star Trek 4, Star Trek saves the whales.
Yeah.
Hilarious. But at the end of it, Dr. McCoy gets off a great line about, the one universal constant is a bureaucratic mentality. Now, in that sense, he was talking about they're probably going to assign us to a freighter because we've been, disobedient to orders and whatnot. And of course, they get the rebuilt Enterprise. But there's many things you can talk about. The bureaucratic mindset includes we know basically everything there is to know. Maybe we do a little more science to like kind of fill in around the edges, but we know basically everything that we need to know. Another bureaucratic mindset is just overly simplistic thinking, right? So the stats are okay. 3 eruptions. Let me see if I can do math right now. It's not a given. 3 eruptions. So there's like one was 600,000 years ago. One was probably about 1.4 million, and one was maybe 2.1 million years ago, give or take. Huckleberry Ridge, probably. It's like Huckleberry Ridge, Lava Creek, and I forget the other name. Are the 3 eruptions.
Okay.
So, and I'm probably getting Huckleberry Ridge wrong. I think Huckleberry's involved. It's your Huckleberry. That's all I know. But, so the math works out. Well, okay, there's been 3 eruptions and it's been between 600,000 and 800,000 years between them, which I mean, if there's only been 3 eruptions, so I probably did the math wrong. It's probably like, let's say it was 2.0 million, 1.4 million, and 600,000 years ago.
Okay. Yeah.
It's between 600,000 and 800,000 years because once it was 600,000 years and once it was 800,000 years. And it's been 600,000 years. Panic!
Yeah. Yeah. We're due.
Yeah. Well, then we circle back to, but it's gone off 3 times, and none of these volcanoes in the whole Snake River Plain complex have gone off more than 3 times in the same location. I mean, don't quote me on that, but I'm pretty sure that's the case.
Okay.
So it's probably what it's due for is probably packing its bags and moving into Montana and just, vacating this current, epicenter of volcanic activity.
Okay.
And then you'd have to go check the tape and see, okay, well, how long does that usually take? I don't know. It might still only be 600 or 800,000 years between times. So we might be due, but it might happen in, whatever that town off the northeast entrance of Yellowstone is, rather than in Yellowstone itself.
Okay.
So it's utterly unpredictable.
It's utterly unpredictable.
Yeah.
Okay.
Yeah, I mean, in the long term.
So don't sell the ranch.
Yeah.
Don't sell the ranch right
up there in Bondurant,
Right. Right. I mean, so if anything, that scale happens again, which it probably will, because it's been happening, things like that have been happening in the American West for hundreds of millions of years.
Okay.
Yeah, it's gonna be a bad day.
Mm-hmm.
Very, very, very bad day, followed by a bad week and a bad month and a bad year and a bad decade, and probably a few bad centuries for the human race.
Oh,
It would not be great.
Yep.
We'll stop worrying about global warming for a while. That'll be for darn sure. We got all that debris in the atmosphere, and we have a, quote unquote nuclear winter. Which would be really funny to call it a nuclear winter because we've had volcanic and asteroid induced winters many times on this planet and never a nuclear winter, thankfully. Hopefully it stays that way, but that's the metaphor we think of.
Okay.
If we did blow a lot of debris into the atmosphere with a nuclear weapon, it would block out the sun and it would cause global temperatures to plummet. So there was a volcano Tambora, much smaller deal. I mean, orders of magnitude smaller deal than Yellowstone. Still a gargantuan violent volcano. But Yellowstone would be 100 or 1,000 times that. So it went off in, I think, 1815, which was known as like the year without a summer in New England.
Yeah.
In New England.
Right.
Because this is Indonesia,
Mm-hmm.
is where this volcano exploded.
Right.
So dust, planet-wide dust storm.
Mm-hmm.
There was snow on the 4th of July in Massachusetts and crap like that.
Okay. So crops must have failed.
It was a bad year.
Okay.
It was a bad year.
Mhm.
So yeah, and people moved out of New England. It, probably sped up the settlement of the Midwest, which was for whatever reason wasn't quite as hard hit. Or people just up and moved because they were tired of plowing rocks up in Massachusetts, and this was just the last
This was the final
final
straw.
insult.
Yeah.
Yeah. But I mean that happens, right?
Mhm.
So that sort of thing happened. I mean, even Mount Pinatubo, I think in 1994 measurably impacted the atmosphere.
Okay.
So, and that was far smaller than Yellowstone.
Okay.
So,
Okay. So when you say pack its bags and move up to Montana, I mean, you're this, so a caldera, is that the right term?
yeah.
Okay. This is a subterranean and subcrustal mass.
Would not be subcrustal.
Not subcrustal. Okay.
Yeah.
And what is it?
It's embedded in the crust. It's embedded
Okay.
in the shallow crust. That there's a crater is literally a hole, or a
Mhm.
caldera is literally a hole.
Okay.
So there is a giant depression. It's a shallow, wide depression.
Okay.
That the park is basically in,
Uh-huh.
which was created largely by a whole lot of semi-solid material being blown out by gas pressure, making a giant dusty explosion
Okay.
that covered Kansas and meters of ash.
Where's that pressure coming from? Like what?
Gas.
Okay. Okay.
Yeah.
Gas is being contained by the crust, and then eventually the crust can't contain it anymore,
Right.
and it blows its top.
Yeah. So everything inside the earth that melts in the presence of some volatiles, some combination of water or carbon dioxide and some other more exotic things. And so when the magma is hot and under high pressure, the gas is dissolved in the magma. When it reaches the surface and starts crystallizing, the gas comes out of solution, separates, and creates basically the driving pressure for eruptions.
Okay. Okay. So it becomes denser, right?
The
It
magma becomes
dissolves.
denser as the gas leaves it.
Okay.
And the gas becomes, this separate phase, it's called, that's much lighter.
That's okay.
It takes up
Hence the pressure,
a whole
right?
amount of space. Yeah,
Yeah.
huge amount of space.
Okay. So the gas was dissolved and then
Yeah.
and therefore dense, and then it de-dissolves, right?
Yeah,
And therefore needs a lot of room
yeah,
and blows the top
yeah.
of the crust.
And this process, sometimes in older literature, was called, or at least it's akin to a process called second boiling, which is kind of counterintuitive. Where if you cool something, it effectively boils. Gas comes out of solution and creates boiling. So yeah, magma is interesting and counterintuitive in some ways.
Okay.
The way it behaves.
Gotcha.
So all of that. Yeah. So I mean, if and when something even vaguely the size of one of the Yellowstone or one of the big yellow, because there have been smaller ones. There have been smaller side events every few, I think, tens of thousands of years.
Okay.
Even one of those would be a pretty bad day.
Okay.
Obviously, it would consume all of that infrastructure that the Park Service is, so thoughtfully built over the years, in Yellowstone itself.
The wooden trail by the hot geysers.
Yeah.
That's a goner.
I mean, I don't know if it would wipe out Jackson Hole, and I don't know about your clientele's feelings about wiping out Jackson Hole, the volcanic eruption, but it could happen.
It would drive down local real estate values.
Right? Right? Well, I don't know. I mean, if it was just, regionalized up there, maybe they'd all move to Lander, right?
Right. But we're in for at least a bad year. Even a minor eruption would result in a very bad year and possibly a bad few years, right? Because you have, so it's dust in the atmosphere.
Dust in the atmosphere. I mean, it also releases gas. So it releases sulfur compounds, and then depending on the volcano, so Iceland is just one mass of volcanoes, right? So, and there was a huge eruption, and I think it was 1783, from, I want to say it was called Laki, but don't quote me on that. I say that a lot because I just can't remember stuff. But I'm just trying to juggle 6 classes right now, like I was.
Oh yeah.
Yeah.
Right.
But that disgorged a whole bunch of fluoride gas. That's bad.
That's bad.
So have you ever heard of hydrofluoric acid?
Mm-hmm.
Yeah. I mean, it would be akin to that at least.
Mm-hmm.
The book, I remember the book I was reading about this saying it was fluorine gas, which could not have been the case. Chemically, that could not have been the case. It must have been fluoride of some kind.
Yeah.
Which would mean probably hydrogen fluoride, which is just awful, lethal, and it killed countless numbers of sheep. And then people eating mutton from those sheep also got, this like fluoride, poisoning basically.
Jeez.
Because, I mean, toothpaste is one thing, but if you, eat fluorine is the fluoride ion is definitely poisonous. Fluorine will kill you in other ways before it has any chance to poison you. It will burn you. But fluoride is poisonous.
Okay.
So it is something that people around volcanoes are susceptible to. So I don't know if Yellowstone would put out gas like that.
Right.
That would be a really bad day.
That'd be a bummer.
That would be a huge bummer. The sulfur compounds are bad enough in their way. So
okay.
Yeah.
Gotcha. Yeah, I think I told you about one of the early science teachers here at the college said to me, he said, yeah, honestly, if the caldera blows, I kind of want to be here at the edge of it because 2 reasons. He's like, I'm not sure I want to live in a post-caldera eruption world because it's going to be a tough world to live in. He's like, also though, when that thing really goes, the 10 seconds I'm going to live long enough to see it is going to be a really entertaining 10 seconds, right? As you see the earth rip itself apart before swallowing you. You're like, yeah, that'd be something to see in your last moments of life.
Yeah. Just enough to hopefully make peace with your maker.
Right.
And
just be like, damn, what a show.
And then get scoured by the super hot cloud of debris. Yeah.
Okay, so you wouldn't be crushed to death. You would just be burned off.
It could go multiple ways, right? So in 1902 in the Caribbean, I forget which island, the Martinique maybe. There was a town in the Caribbean that was like 20,000 people at an opera house. Of course, freaking Madison, Indiana had an opera house, so it doesn't impress me as much as it once did. Gosh, what was it called? Was it called St. Pierre or something? But anyway, so the volcano up at the top of the mountain went off, and the town was just leveled by these, and they're usually called by the French name nuée ardente, or glowing cloud or burning cloud. Sometimes they're called glowing avalanches.
Right.
But they just roar down the side of the mountain. They're just superheated rock dust. Traveling really fast. And they can just level things. Like the only people who survived was like one guy in a rowboat, I guess, out in the bay, and then one guy in the basement of the jail, which was solidly enough built that he didn't get killed.
Right.
Everyone else was just
gone in a matter of 3 or 4 seconds.
it's hard to say.
Yeah.
I mean,
Right. We only have the guy in the jail and the
Yeah,
guy in the rowboat, you know?
yeah, talk to. It seemed to be pretty quick for most people. Yeah.
Okay.
Yeah. But
Huh.
that's, yeah, that is one of the things that style of volcanic eruption is liable to.
Mm-hmm.
Yeah. It's called Mont Pelée.
Wow.
But yeah. So how are we looking on time?
Well, I think we're about a minute 20 so far. I mean, an hour 20.
Okay.
Okay.
Yeah.
Yeah.
I just
Are we
realized I need
are we
to-
recording? I just see all the zeros on the screen.
zeros?
At the
Up
top of
here.
the mixer board.
Oh, yeah. So it's recording through this.
Oh, okay.
I
Gotcha.
just realized I need to plug my power cord in.
Okay, no worries. Are you on a time? Do you have a time crunch?
Really?
Okay.
It's pretty fascinating.
Yeah. Yeah. I'm just trying to keep up. Okay, tangent. Well, no, forget tangent. We're just gonna take a left-hand turn.
Okay.
A couple of weeks ago, you and I almost had a chance to talk about AI,
Okay.
and then we got interrupted by, I don't know, some speech at a dinner or what have you.
Sure.
You were telling me that the AI project has been something like 100 to 80 years, 80 to 100 years in the making.
And see, you send me this sheet to prepare for it, and it's like, wow, did I say something like that? I mean, what was 80 years ago was ENIAC, right? Was the
Okay.
first computer,
Uh-huh.
and it was being used for things that, were the beginnings of what we're trying to use AI for. But
Hmm.
at the time, it was trying to do calculations faster.
Mm-hmm.
And that's what AI does.
Mm-hmm.
It runs on statistics. It
Okay.
just runs on ever more sophisticated flavors of statistics. Like even a neural network, it's
Mhm.
doing statistics problems.
Okay.
It's just doing them in a really arcane way that no human being could sort through all of the individual components of a calculation, even if they wanted to.
Okay. We're talking. It would take you billions of years to go through all the calculations.
I mean,
Yourself.
yeah, if we want to throw a Carl Sagan billions at it, yeah,
Sure.
basically.
Mhm. What's the difference between that? What is the difference between what AI is doing versus what a human being does, right? People have said to me, "Oh, it's the same thing. It's just pattern recognition." And human beings and their brains are trying to do pattern recognition,
Right.
and AI is doing pattern recognition just trillion times faster. Is that true, or at least in some sense?
That's really, I mean, that's a crude and oversimplified way of putting it.
Okay, so it has some merit, but it's
Yeah,
crude.
yeah.
Okay,
It's
what
crude.
can you tell us what a human brain does that an AI isn't doing?
I mean, if I could do that, I'd probably have a Nobel Prize in physics.
Okay.
I mean, that is the name of the game.
Hmm.
So we talk about neural networks. I mean, that's still, sorry.
So I think my computer cord's back at the house. I'm
Mhm.
gonna run back and grab that so this doesn't die.
Okay.
So you can
Oh,
keep
sure.
going.
Okay.
So
Okay.
We
Sounds
got
good.
enough juice to
yeah,
last the 20 minutes. Okay.
yeah,
Okay.
we
All
should
right.
be good.
We shall
So-
struggle on in your.
All right.
Okay.
your
I
absence.
apologize. I was looking through my bag. It's like something here.
Yeah.
Thought I'd watch it, but
Oh, that happens.
Yeah.
That happens. Yeah. Um, shoot. AI,
Neural
pattern
networks.
recognition, neural networks. Yeah, I mean, so those are still, as far as I know, the state of the art, and there are many different flavors of them.
Mm-hmm.
And so in some loose sense, those were patterned off of what we do know about how our brains work,
Okay.
which
Yep.
is another one of those things that we, sort of trumpet, like, oh, we know. Like, I remember seeing some Newsweek headline in probably about 1999 saying how we think.
Mhm.
And it's just, and whenever people are talking about that, they're talking about a really high level, sort of following of either electrical impulses or blood flow or something,
Mhm.
and saying that different, regions of the brain light up. Well, that's nice and all, but there's an awful lot. Let's just say an awful lot, a number that should be expressed in scientific notation rather than writing out all the zeros.
Mhm.
Number of cells in your brain, my brain, any human's brain.
Mhm.
And then those individual neurons. Now, we do know things at the individual cell level in terms of neurons have fascinating immensely long interconnections with other neurons. They grow synaptic connections to neurons in distant parts of the brain, which is really bizarre. I'm not aware of any other cells that do anything like that.
Okay.
So we have some idea, at the grossest big picture, what happens when we, think different types of ways or experience different kinds of emotions or, are doing other, or we have some idea what, lower parts of our brain are controlling all the unconscious stuff like breathing, heartbeat, gut function, stuff like that. But
All right, so just I'm going to attempt another analogy here.
Sure.
Just really for the sake of my own understanding. So if I were to, you talk about this Newsweek article, by analogies, it's sort of like saying like, okay, well, here's how do you get from New York to New Orleans, and you just trace your finger along the major highways on a map. That's how you get from New York to New Orleans.
yeah,
Well, that's true.
yeah,
In some very real way,
yeah,
that's an accurate description of how one gets to New York to New Orleans.
yeah.
But if you were to drill, if you were to say, okay, well, that's how you do it, and then, all right, 14-year-old child, go, you're in New York, go to New Orleans.
Yeah.
You'd have to teach them how to drive. You'd have to teach them to navigate traffic. You'd have to teach them how to signal a turn. Like there's so much more involved.
Yeah. Yeah.
And that's something like what's
having
going on.
a roadmap.
Mhm.
That's better than our situation of understanding the brain.
Okay.
We have a like physical geography map.
Oh.
Like, oh, okay. I bet there are roads that go this way.
Okay.
I bet they put a road through the Cumberland Gap.
Right.
That'd be a good place to put a road.
Right. Okay. Right. If I were to put a road, I'd put it there.
Yeah.
So let's assume there is one.
Yeah. 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 So I mean, I'm going to have to get through the Appalachians. I'm going to have to cross, the Tennessee River. I'm going to have to do this, that, and the other thing at a very broad level. Yeah. I mean, it's kind of like if I may try a different analogy, it's like we have an aerial photograph of the Louvre, and then we have 10 bricks from one of its walls. I'm like, oh, this is how bricks get put together. Oh, that's cool. And then here's the whole structure. And that's what we know, right? All that, all the interesting details in the middle, like, the exact layout of the rooms where they have the Egyptian exhibit.
Right.
That's a little much
right
now for what we know about the brain.
Okay.
So we have, and so these neural networks have been built on the pattern of, okay, neurons do these things. Cool. Well,
Okay.
let me link neurons, which are just holding cells for numbers, with, other neurons via these pathways that are just, numeric operations. They're just arithmetic operations.
Okay.
And then let them, and then set up a scheme that encourages them to, you feed them a bunch of data, you backwash it through that system, and you sort of leave this residue of, oh, okay, well, if all of these cells had these style of interconnections, I would get something that reproduces the original data reasonably well. Okay, well, then let me do it with even more data, and hopefully that'll get better. And then let me feed it new data and, try the forward problem and see if it provides the right answer that I already know for some other reason. And so these neural networks can do things that no other algorithms can do.
Okay.
That we have yet to discover. So they're interesting from that perspective. And are they pattern matching? Is there got to be at some really, basic level, some similarity with what we do with our sensory input? Since we patterned the thing off of how neurons work, it seems likely. But I mean, and that said, our brains are still far better at pattern recognition than AI is right now. That's still got a ways to go. There are things that the various kinds of AI, all of the different statistical mechanisms that we have for, solving problems like this, all of them can do things far better than the human brain, certain types of problems. They're not biased in the same way that we are. They don't get emotional attachment to certain outcomes. They don't jump to conclusions the same way that we do. They don't impose a pattern that's not there in the same way that we do. I mean, they can do that. They definitely can do that. But there are certain types of statistical problems where they will simply give us a better answer because they're able to navigate a middle course where humans want to jump to an extreme, want to say it's all this or all that, things like that.
Okay. Why? I want to go in multiple directions right now, so I'm gonna have to
Sure.
I'm just gonna have to just choose. Um, if I ask an AI to write me a children's story, it can do it, right?
Yes.
From what my friends have told me who have experimented with this to some degree, they say, yeah, it can write a children's story, but that children's story is just, it is a children's story. It's also kind of dumb, right? It hasn't captured the delightfulness of a really inspired children's story. And then,
Sure.
Novel or movie script, the problem gets worse, right? What what's going on there, right? That it can produce this story in seconds, right?
Sure.
Whereas if I wanted to produce even a mediocre children's story,
Right.
it would still take me an hour, right?
Oh yeah. Yeah. Even if you just dashed off what came into your mind and like, yo,
Right.
I can write a Curious George story. I know the formula.
Right.
Yeah, it would do that a lot faster because
Yeah.
it can manipulate symbols far faster than we can.
Okay. Why why are human brains so slow in certain ways, right?
Well, I
Like,
mean, in the scenario you're laying out here, what our problem is that we rely on our appendages to go write things.
okay.
Whether even if we're typing at a keyboard,
Uh-huh.
we're still, if we could simply record our thoughts
Uh-huh.
the way that a computer can record its quote unquote thoughts,
Yeah.
we would the difference would be a lot less at least.
Okay. Okay. We could push it out. Yeah, we could, right. You and I could probably imagine a children's story in 5 or 6 seconds.
Well, I don't know about that, but it would be, where you were saying it was an hour. Maybe I could think one through in a minute.
Okay. All right. So one order of magnitude then.
Yeah.
Yeah. 60 versus 6. All right.
Yeah.
Yeah. So is seem fascinated with AI.
Yeah.
But I remember reading an
People
article.
have been brought up watching Star Wars with this kind of irresponsible tendency that 20th century media had to like, oh yeah, these robots, they'll just be like people.
Yeah.
They'll be like C-3PO and R2-D2 and
Right.
and Data on Star Trek: The Next Generation, and they'll have personalities.
Uh-huh.
They'll have personalities that aren't personalities, but they are personalities, and that makes them endearing. And it's kind of garbage. But
Right.
we've been fed that.
Big Hero 6 and
There you go.
what was that Disney movie that they made? Was it Wall-E? Yeah, Wall-E.
Wall-E. Yeah.
Uh-huh. So this article I remember reading, and I hope that it got its history right, but I think it did. When penicillin first came out and the first antibiotics were being discovered,
Sure.
people were super excited. They're like,
Yeah.
whoa, at best, for most of human history, we've maybe gotten to a draw with disease. Usually we're losing, but at best case scenario, and all of a sudden penicillin comes along and then other antibiotics come along. And all of a sudden everyone, and this was the early 40s, I believe.
Yeah, it was in the 40s.
Yeah. Everyone got really excited, like, oh man, we're winning.
That's right.
And we're winning. And we're winning so well that I bet in 50 years we'll have won.
There will be no infectious diseases anymore.
Right. And now here we are 70 years later, 80 years later almost, and we definitely haven't won. Right.
Right.
So right. So there's that one thought group in my head of like, whoa, penicillin came along and people said, if current trends continue, right. And they extrapolated
that's
way
the
out.
bureaucratic mindset right there. Like, it's been 600,000, 800,000 years. Well, of course, only.
Right. You would have looked around the biological world and said, we are definitely the only things doing this.
Of the abiotic world. I mean, what rock is doing arithmetic?
Right.
And then somebody had the idea of building a difference engine, Babbage or whoever. And then in the 20th century, we finally got, okay, gears are not going to do it. Electronics, tubes and transistors are going to get this done. And they did. So now they do. So now the vast majority of mathematical calculations are performed by machines. And no human even knows what the outcome of it is directly. We only see the outcome of a billion calculations, and it's like, moving my character in Call of Duty or something like that.
Okay. Gotcha.
So
Gotcha. We set some things in motion, then we wait on the other side of the gate for the outcome, right?
yeah.
Right.
Yeah. And that's the thing. I mean,
It began as something like, if I want to multiply 5.72 by 3.8 to the 16th power, I could figure it out.
Yeah.
But damn, it's going to be boring and it's going to take a while.
It'll take quite a
Let's
while.
send a machine.
That.
But I can check it.
Right.
Whereas now we were sort of the audience of math. We're a mathematical audience.
We're the coder is now setting things in motion that, he can't check. He can't check directly. He can implement some other pile of code to do other things that he can't check directly, in order to perform a sort of high level check on it. I mean, since this code over here and this code over here don't have anything directly to do with each other, if they come out with the same answer with the same problem, and I believe they are both written to come up with this, I believe this other one is written to come up with the right answer to this problem. And this
They're
one
both
over here
honest.
comes up with the same answer, then that's the best I can do. I mean, yeah, it is a world where that's the thing. I mean, people want to go all the way to the extreme of AI is going to take over the world, and it'll be like the Matrix or something. Like, where's it going to come up with the directionality to do that? Because I mean, the fingerprints of humans are still going to be all over it. But at the same time, yeah, it is going to get out of control in certain ways. I mean, certainly, to come back to your antibiotics example, which is a great example, so antibiotics are great, but at that time we had no idea how important the gut microbiome was. And now it turns out, oh, okay, so we've been administering people antibiotics and basically taking shotgun blasts to their colon, basically over and over again whenever they get an infectious disease. And now people are getting like, why is it that there has been an exponential increase in food allergies and things like that?
I see.
Maybe that's related. Maybe that's related.
Right.
So, it's had unintended consequences. The internet social media has had unintended consequences.
Right.
I mean, social media was, of course, invented to make money and convey advertisements. The whole, inducing anxiety and, causing people to lead miserable lives, I don't think was intended, but
But here we are.
But
right.
here we are.
What was it? I think it was Jonathan Haidt came out with a book saying, 1 in 5 teenage boys report, feelings of intense depression and thoughts of suicide, and like 1 in 4 teenage girls report something similar. And he's just like, where is this coming from?
Yeah.
Right. And his explanation was largely social media.
Yeah.
And it's like, what the hell? Right. Zuckerberg wasn't sitting there at Harvard in 2006 being like,
how can I make as many people as possible mentally ill?
Right. Exactly.
Just thinking about how I can make Scratch.
Right. What's going to pay for the yacht?
Right. Exactly. And then the second yacht. And then the trip to space. But
right. Yeah. Huh. So I mean, can history, especially scientific history, teach us a general axiom, a general principle for when we look at new innovations? Like, is it overly cynical to say like new innovations are significant, but never as significant as their proponents, right?
I mean, there's always people who think that something is, there'll always be a significant number of people for any major development that oversell it. I mean, that's inevitable.
Right. That's this will usher us into paradise.
Humans are salesmen. So there will always be a certain.
I
fraction.
can't argue with that, you know. Wyoming Catholic College, this house. Yeah,
That's right.
I've been selling stuff for the last 15 years of my life.
That's right. Yeah.
Yeah. The Green Dragon podcast.
Yeah. Right.
It's well, you'll learn everything you need to know. You know?
That's right. Yeah. Yeah. Exactly.
Huh. Right. Okay. That's interesting. Humans are salesmen. Right. Which actually itself might shed light on the AI problem, right? Like our brains are kind of solution oriented,
Mhm.
whereas you're saying AI has a certain detachment from solutions to just data. Like, yeah, this is what
I mean,
this is what we conclude.
it does what it's coded to do. I
Mhm.
mean, there are people who talk about emergent behavior,
Mm.
which is, yeah, I mean, that once you've written a million lines of code, stuff starts to get difficult to predict. Like, oh, wait, I told it not to do this, but then there's these other 15 subroutines that it could have, gone down instead for
Okay.
actually very good reasons.
Okay.
And that might produce an unexpected output.
Okay.
So that does, I mean, that's been happening since, gosh, probably like Windows 98.
Okay. Where
Just
again
because
we became sort of an audience of our own creation. Like where it's
to an
like,
extent.
okay, we're gonna hit the pinball and then we're gonna run to the other side of the box and watch what comes out. And
Yeah, no one person can keep track of it all.
right, everything we put inside, is too much for our predictive ability.
Yeah. So despite the fact that it is in fact, going through a completely what's the word I'm groping for? Deterministic, sequence of algorithm steps, no human being from the outside, even I mean, what am I saying outside? Even the ones that wrote it, because it's ones plural.
Yeah.
But even a single person writing it all couldn't carry it all in mind. And follow it all the way through to a conclusion.
Right.
But yeah, so that's so stuff is going to continue to build on itself, and it's that's the fact that our creations, we can't keep track of them. That's going to just continue to build. And where that goes, is it going to go to the Matrix? I doubt it. Will there be negative outcomes to it? Certainly.
Right.
So,
Right. We've never enacted a change without some negative outcomes.
Oh yeah.
Right. The agricultural revolution came at cost.
Yeah.
The invention of the city came at some cost, right? I think it was his Father James was telling me that in medieval cities, the death rate always exceeded the birth rate, right? In medieval cities.
People have to move in from outside.
Yeah, people have to move in from the outside, right? Until sanitation has caught up. You can make more money in the city, but there's a very significant chance that you're just going to infect yourself to death inside of a city. Right.
Yeah.
Right. And on the other hand, you can't get the economic development that affected all of Europe and then all of the world unless you have cities, right? You have to bring that many people together for certain things to take flight. Right. So you're constantly in this trade-off game. Yeah. I guess Thomas Sowell is famous for saying it. There's no solutions. There's only trade-offs. But I will say my twin brother said that to me something like 15 years ago. And I thought it really stuck with me. He's like, yep, everything's a trade-off, Yeah, we're constantly.
There are some trade-offs that are so obvious. Of course, I'm going to make this trade-off that they become solutions. But yeah, everything does have a cost.
Right.
Everything has an opportunity cost.
Yep. Yeah.
So
exactly. Right. I can become rich by working 80 hours a week, but working 80 hours a week.
And then I will get one of those mental problems we were talking about earlier.
Yeah. Right. But on the other hand, if you don't work 80 hours a week, you might, come into your 60s being like, well, I might be able to retire, but I'm not going to have the retirement that other people have,
Yeah, exactly.
Right. I enjoyed myself.
Hopefully I'm not too crippled up by that point to enjoy my retirement if I have been working 80 hours a week.
Sure. Again, kind of working through some of the topics we talked about before, and you're good on time?
I'm good on time.
Okay. We had another conversation. I think it was in like the parking lot of Holy Rosary or something like that. And we just mentioned briefly, global warming, a few other questions. And if I recall correctly, you said, well, we're in an ice age. And I was like, whoa, wait, what?
Oh, sure. Yeah.
And then like we had to like go help the Knights of Columbus serve pancakes or something like that. And
Yes.
I was like, wait, what about this global ice age?
Yeah, exactly. I just dropped that on you.
Yeah, exactly. Like, global ice age.
Mic drop.
Yeah, exactly.
Well, I
no,
mean-
no wonder I want to move south.
Right. Well, I mean, if you take the long view, right, and being a geologist, you try to take the long view on things.
Mm.
The fact that there are permanent low elevation ice caps on the planet
Mm.
means that we're in an ice age.
Mm.
Period. So that's unusual. That's not the planet's normal situation.
Mm.
So, I mean, it's not that abnormal a situation, but probably a majority of the time that's not the case.
Okay.
So, yeah.
So if the caps melted, it's not a big deal.
Well, I mean, it would be a big deal because it would drive us, out of the equilibrium that we've had for the last 2 or 3 million years,
Oh,
in
okay.
which, let's just put it this way, human beings came to be during that period of time.
Okay.
Um, and so we would be dealing with a world that we've never dealt with.
Hmm.
Mm.
We can look at the geologic past and see what it was like in certain ways. But yeah, I mean, if we melted them all and went back to a, Eocene thermal maximum world, well, first of all, the whole reason ice caps come into existence is because of the distribution of continents. So if we could melt them all with our current distribution of continents, that's a little drastic because this current distribution of continents is set up to be an ice age.
Ah,
So
Okay, you got to unpack that a little bit more.
Sure.
Like, give us a few more details.
So what do we got right now? We've got Eurasia, and Eurasia butts up to one side of the Arctic Ocean.
Mm-hmm.
And then North America, also a pretty large continent, butts
Yeah.
up to the other side of the Arctic Ocean.
Okay.
The Arctic Ocean is pretty small.
Yeah.
So the land comes up fairly close to the North Pole
Yeah.
and surrounds it.
Yeah.
And there's just this one fairly shallow, fairly feeble little ocean there at the North Pole. And then at the South Pole, there's a freaking continent sitting right on top of the South Pole.
Right.
So that's been frozen for a long time. Antarctica has had ice for, I don't remember. And in fact, it's probably debated, but let's say 10 or 15 million years, maybe longer.
Yeah.
And then as the continents have closed in on the North Pole on the other side, then we have freezing at both ends.
Mm-hmm.
So we could have the Arctic Ocean full of pack ice. We could have glaciers form in Canada and Siberia and the Nordic countries and all those places. And so we're in an ice age. And so ice ages have cycles.
Mm-hmm.
So what we normally mean by we're not in an ice age, what the normal layman would think of as an ice age would be a glacial maximum.
Okay.
So we're 30-some thousand years out of the last glacial maximum, which is when, ice is in southern Indiana.
Whoa.
Yeah. So the ice is now in northern Canada. That means we're in an interglacial. We're still in an ice age in the
Mhm.
geologic sense, because there's still permanent ice,
Yeah.
at low elevation.
Okay.
But it's also receded, way back. There's not, Antarctica is not surrounded by 1,000 miles of pack ice, and the Arctic Ocean is not permanently frozen over. And there isn't, again, I mean, and of course, North America kind of has this channel where the Great Lakes are that kind of ushers ice south. So I think southern Indiana is probably about as far south as the ice was, like around the entire northern hemisphere. But it's where I'm from, so it's a point of reference for me. But yeah, so I mean that's what I meant by that remark.
that's
Right. Let's go serve some pancakes, Jonathan. Yeah. Let's go celebrate the ice age.
But if we get in the Wayback Machine and we go back to the Cretaceous, so the continents were strung out along the equator,
Okay.
and so there are poles, and
Yep.
there's like thousands and thousands of miles of ocean until the nearest continent. Nothing's going to freeze in that circumstance.
Okay. There's too much kinetic energy in the water.
I mean, yeah, the water evens its own temperature out,
Okay.
and it also absorbs heat. I mean, there's a whole bunch of factors that I'm not master of all of the different factors there.
Okay.
But basically, if you have land strung along the equator, which for lots of periods of Earth's history it has been, you don't have glaciers.
Mm-hmm.
If you have large amounts of continent near or on the poles, you have glaciers.
Okay.
So
Okay.
there was some ice
Because
ages in the
Earth,
Paleozoic.
because the Earth uh just prevents the water at the top and bottom of the globe from absorbing heat from other
Well,
parts of the ocean.
The ocean can swap heat with itself very readily.
Okay.
Land can't.
Land can't. Okay. Right. A hot patch of dirt over here doesn't really help a cool patch of dirt over there.
So,
whereas water interacts much more readily.
And water has this actually kind of psychobilly property that it gets denser as it cools down to about 34 degrees. And then it gets lighter. And then, as we all know, ice is lighter than water. So it floats. So that means instead of the cold water just sinking to the bottom and freezing,
and killing everything,
which is what any other chemical substance would do almost, water's like, oh, well, let me take that really cold stuff and that solid stuff and put it on top where the sun can hit it. And then it will melt again. And, and then the density cycling will happen. And so the bottom of the ocean is like 2 degrees above freezing. And it's perfectly happy like that. And it stays liquid. And then if anything gets down to that temperature, it sinks down to the bottom and displaces some of that water, and it has to go up.
Right.
So it just doesn't want to freeze. So only when it's being hedged by land can it really get to a situation where it freezes. I mean, it also has salt in it.
Right.
So it also doesn't want to freeze. There's not much salt in ocean water, but it does depress the freezing point a little bit. Make it even easier for this to avoid freezing.
Right. Right.
The Earth has had worse ice ages than even the glacial maximums we've had in the last 3 million years.
Why do you say worse? What
down to lower latitudes?
As in it's
the equivalent of Florida being under a glacier.
Okay. All right.
At least,
and it's less amenable to life.
Yes.
Yes.
Yeah. That would be putting it mildly. Yeah. Although ironically, that period, the snowball Earth, is the late Precambrian, and it actually immediately predates the Cambrian explosion. I mean, immediately, maybe it's 100 million years gap. But still, in the grand scheme of things, it's like that's weird that episode would come before multicellular life finally, like lights a torch under itself and like starts, really going to town. So it's one of the strange, like, is it a coincidence? There have to be a certain number of coincidences in the world, in some sense. But is that one? From whenever you come up to an individual one, you just have to ask, did this happen by chance? Or did one lead to the other? Whether you look at it from the efficient cause standpoint, did one lead to the other? Or was there a reason why, if we look at it from a final cause standpoint, right? Yeah. Huh. That's funny. Yeah. But so the snowball Earth, I mean, if you push the idea too far, it may be too far. It's not, there's no guarantee that it's too far. Maybe the entire Earth was covered.
Wow.
I mean, maybe it literally was a snowball Earth. Or maybe it was just that there were glaciers down to, I don't know what the geologic evidence is, because you have to match glacial deposits to paleo latitudes, and paleo latitudes are not the easiest thing in the world to get. But that gives you the idea, okay, this is something that was deposited by a glacier and it's at, 30 degrees paleo latitude. It was within 30 degrees of the equator at that point.
Okay.
That seems pretty extreme. We don't have any evidence of that happening since the Cambrian explosion.
Right.
So that means a lot of the Earth was probably covered with glaciers. Maybe probably the majority of the Earth's surface was frozen.
Yep.
With probably some area around the equator open.
Yep.
And of course, we're also talking about rocks that are at least 600 million years old. So there aren't as many of them, and they aren't in as pristine a shape as we would like.
Okay.
Draw conclusions from.
Right. Because they've been traumatized for the last 600
traumatized. Yeah, that is one class in field science. There was always that class that I told students not to date traumatized rocks.
Not a good
It's words to
experience.
live by.
Yeah, yeah.
Yeah.
Mhm. I think we just found the title for this episode. So don't date traumatized rocks.
That's right.
Mm.
Yeah, that will describe a fair amount of what we were talking about.
Mhm.
So
Do you think that there was ever a period that the equator was so hot that it was impossible for life or mammalian life?
well, yes,
Hmm.
although mammalian life was not a glint in the eyes of nature at that point.
Uh-huh. Yeah, okay.
We're talking about so when the Earth presumably condensed out of the original solar nebula,
Hmm.
um, maybe it condensed slowly enough that it lost its heat to space,
Hmm.
and just became this pile of rubble.
Hmm.
Or maybe it accreted fast enough that, when you shoot a bullet into a, hunk of metal, it's hot, right? Because all that kinetic energy got turned into heat,
Yep.
or a lot of it did.
Yep.
So it's possible the Earth had some residual heat just from that. But even if it didn't, it was still seeded with a lot of radioactive material.
Ah.
The early bodies that formed in the early solar system have traces of things like aluminum 26,
Uh-huh.
radioactive elements that are just not present in the solar system anymore unless we make them in atom smashers.
Okay.
But the daughter elements are there
Sure.
in the places we would expect for the parent element to have been.
Yep.
And so that was a source of heat that's no longer present.
Okay.
Right. So it seems like the solar system was seeded by probably a supernova. That's where you get all these weird isotopes from.
Yep.
Immediately before it condensed, and that was presumably because of the shock wave from the supernova. So the story kind of all hangs together. Um, and so the early solar system was, had very hot bodies.
Right.
Okay, I'll get past that. So the Earth would have condensed from this material that's very radioactive.
Yeah.
And so even if it condensed cold, i.e., the pieces collided and then radiated their heat to space, by the time the Earth got to some sizable fraction of its current size,
Hmm.
it would have started melting on the inside just from the radioactivity
Hmm.
because it wouldn't be able to lose it to space.
Yeah.
So the larger the body is, the more geologically active it is because the more heat it can retain.
Right.
So Mars is dead. Mercury is dead. They have Mars probably has like the occasional last gasp of some sort of igneous activity, but Mars is basically dead geologically. It doesn't do anything. Whereas Earth has volcanoes and earthquakes and the whole 9 yards, and is clearly a planet that's open for business.
Hmm.
Mercury, despite being close to the sun, is small and cold and dead. It
Hmm.
does not have active geology. Venus is close to the size of Earth and is pretty hot, so it probably has active geology, although since there's no water at the surface, that changes a whole bunch of things.
Hmm.
Um, but Earth is open for business. Earth is doing stuff. Earth is still in its prime.
Is
So,
it a younger planet than those?
no, it's a larger planet.
It's a larger planet. Okay.
If you're a larger planet, you're on a longer time trajectory.
Hmm.
What about like Jupiter then? Do they
Well,
have
Jupiter's a gas planet, so it's doing all kinds of stuff.
all sorts of stuff?
So, and it's also gargantuan.
Yeah.
You don't want a vacation on Jupiter. Yeah.
Yeah. It's a little hostile. It's a
Yeah.
little hostile.
Uh-huh.
I mean, although, Earth in some sense. So the guy, he may have retired by now, but he was at least for a few years the head of the Vatican Observatory,
Hmm.
who was a American Jesuit. I think the one before him was an American Jesuit,
Hmm.
but Guy Consolmagno, who's actually on my podcast once. It's amazing who'll say yes if you ask him, right?
Hmm.
But he wrote a textbook that I used to teach one year, and he uh he had this thought problem. Now, suppose in that era we didn't know about exoplanets.
Mhm.
The fact that we know about exoplanets, by the way, I'm still geeking out about that and always will be, because I lived in the 20th century when this was just like the glimmer in some science fiction writer's eye. And now
Mhm.
we're like, oh yeah, there are this many of them, and we're discovering more all the time, and we're learning things about their atmospheres and blah blah blah. So if you wrote this problem today, you would phrase it in the terms of, oh yeah, if you're observing an exoplanet with your telescope and you see the chemistry of their atmosphere is like this. Okay, here's a planet that has no atmosphere, probably not hospitable to life. Sure. Here's another one that's got like, I don't know, 50% nitrogen, 45% carbon dioxide, 5% water vapor. sounds okay, right? And then here's a third planet, and its atmosphere is some combination of, oh, let's say nitrogen, argon, and fluorine gas. Now, fluorine gas will set water on fire.
Mm-hmm.
It is the most reactive element on the periodic table if you purify it. It
Mhm.
will rip electrons from anything,
Hmm.
including oxygen, which is second worst.
Uh-huh.
That third planet would be the planet you would look for life.
Because
Because the
There-
only thing we
there's so
know
much
that does
going on.
psychobilly chemistry like that, like purify the most or the second most electronegative element on the freaking periodic table,
Hmm.
is life.
Mhm.
Life is the only thing that does extreme psycho bonkers chemistry like that.
Right.
Wow.
Only life.
Uh-huh.
Only life.
Uh-huh.
Wow.
Nothing else. So if you found that situation, if you found free fluorine gas around a planet somewhere, that's where you would look for life, despite the fact that it would destroy all life on this planet on contact. But when single-celled algae started putting oxygen into this atmosphere, it was a global holocaust.
Hmm.
How many of their friends, neighbors, and relations did they destroy? Nearly all of them. I mean,
Whoa.
that's a mass extinction on the level that we cannot dream of.
Sorry, hold on, back up. When single-celled organisms
Yeah,
started
cyanobacteria.
putting oxygen into
Yeah.
our atmosphere,
Right. No,
It-
it took them several hundred million years to get there, but
there was a holocaust of what? Of other single cell
of other bacteria
that were like anaerobic.
yeah, anaerobic bacteria. Yeah,
Okay.
yeah, which everything at the start of life was anaerobic because
Okay.
well, there's no oxygen. Once you've got oxygen, you have an enormous opportunity and you have an enormous problem.
Okay.
You have an enormous opportunity because you can now make energy like gangbusters. Like the
Mhm.
only way you can have multicellular life is by having something psychotic like oxygen in the atmosphere so that you're just making energy like, like turning a press and turning out money.
Okay. All
Um,
right.
that's the only way you can do that because multicellular life is so energy intensive.
Yep. Yep.
So the problem is you now must spend an enormous amount of that energy you're getting on cellular machinery to protect yourself from the oxygen because the oxygen will eat the organic compounds out of which you are made. Because
When you say eat, you're saying that oxygen will rip,
it will burn it.
it will burn.
Right? I mean,
It'll
basically
pull electrons off of
That's right.
your
That's-
molecules.
Yes. It will
And in doing so,
oxidize it.
destroy
Yeah.
what?
It will turn carbon into
tissue
carbon
that's there.
dioxide. It will turn hydrogen into water.
Mm-hmm.
And they are no longer bound to each other, so they can make all these beautiful, floppy, detailed organic molecules that we need to do all the business that we do.
Mm-hmm.
So we have so much machinery in all of our cells to protect ourselves from the oxygen
Mm-hmm.
that we need for survival.
Right.
So it must be carefully channeled, right? I mean, it's
Yeah.
like a power plant.
Yeah.
It's like a nuclear power plant.
Mm-hmm.
It's so valuable. It's so helpful.
Mm-hmm.
It generates all this heat and all this usable energy.
Right. But
We
don't build
must
your
protect
house next to
ourselves.
it.
But we must protect ourselves from it very carefully. Very carefully.
And
Yeah,
here,
that's why like there's such a thing as oxygen poisoning, right?
Indeed. Yeah.
yeah.
Yeah. I don't know the details of that, but yeah, you put yourself into too much oxygen, too oxygen rich an atmosphere. Yeah. I mean, that and the fact that if you're in too oxygen rich an atmosphere, it becomes even easier to set things on fire. And that could be problematic too.
Right.
So
Hmm.
the explosive limits for all your gases change.
Hmm.
So have they
So we
been-
need things like, so go ahead.
Go
ahead.
I was just wondering, based on the planets they've been finding, are there ones that are getting close to like maybe having life on it?
I mean, I don't think we've seen any that have oxygen, fluorine, I guess chlorine. If somehow life started photosynthesizing chlorine gas, that would also be kind of ridiculous. I don't know of any evidence that we found anything like that.
Okay. I was just curious. That is really fascinating. I hadn't heard that there's something like that out there.
Yeah. Yeah.
But what your basic point is, if you want life, and especially cellular life, you need a planet that have a circus going on, a chemical circus, right? Like you
Right.
need some chaos
Yeah.
where something can get in there and affect some change.
Right.
So in that way, is that movie Interstellar, right? Does it actually hit on something true when they go and visit one planet that's very close to
Mhm.
a singularity, right? And even though there's oxygen and water, they're like life couldn't be here. Things are just too predictable, right? There's the gravitational environment, which is there, is just so stable that you can't get the spark, you can't get the chaos that you need for life. I mean, this is science fiction, of
That
course,
seemed
but
kind of far-fetched when you explain it that way.
oh, okay.
Yeah.
I mean, that is a very good way of saying someone you're full of shit. You know? That seems far-fetched when you explain it that way.
I mean, you'll see all sorts of textbooks if you look at 20th century books about, you know, the history of life, like speculating that the moon somehow had to stir the primordial soup. So if we didn't have a moon to have tides, that wouldn't happen.
Okay.
That sounds like malarkey to me.
Okay.
I finally reached the age when I reread one of those passages. I'm like, and what scrap of proof do you have that that's actually the case? I don't know of any. Um, what allowed life on Earth, so far as we know? I mean, so first of all, life had to get started. We haven't got a clue. We still don't have a clue how that actually happened. There are very smart sounding people, very well educated idiots, who talk themselves, or at least like to have people think that they know how
Okay.
that could have happened.
Yep.
But it's all very high level speculation.
Okay.
I mean, you take what I said earlier about the structure of the brain and then multiply that by another factor of 10. We don't know how life got started. We don't know in what environment it got started. We don't know if it got started on Earth. Maybe it would have been easier for the very first steps of the chemistry to happen, I don't know, on a like organic rich icy body. Eh? Eh?
Yeah.
And then it somehow crashes to Earth, and a few of these like proto cells do a little this, that, and the other thing. It's like that. It's like that Farside cartoon. I think it's a Farside cartoon where the scientist is on a blackboard and he's like doing these equations, and then a miracle happens, and the other scientist standing there saying, "I have a problem with that stuff." um, that's a
Yeah.
little ad hoc. It's a little
Yeah.
ad hoc.
Wow. But there's a chance that we are all aliens.
In a sense, yeah.
Yeah.
I mean that our descent is from, like that life was planted on Earth from somewhere else. I mean, then the term panspermia is or used to be used for that.
Maybe
Right.
find a new term.
Right. Yeah, exactly. Well, yeah. Like a seminary. It's if you look at it too closely, it seems like an unfortunate word as well. But,
right. Yeah, exactly.
it's from the same root.
Right.
It's that a seed has been planted from somewhere. So, yeah. So we just don't know and we don't know how we could possibly bootstrap ourselves up from, even the most interesting organic chemistry that can be created by cosmochemical processes, which there are amino acids and nebula and things like that. That's nice. That's, you know, 99 bricks short of a 100 brick load, though, right? By the time we need to build them into proteins. We need DNA. We need RNA. I mean, just to make the simplest cell that we know about, or even the simplest cell that we can sort of infer back from, I mean, because of course, everything that we have on Earth, including our bacteria, has been winning the evolutionary competition for billions of years.
Okay. So it's made some adaptions that
It's made everything in
that the early
existence is made from
prototypes
sort
didn't
of-
even need.
That's right. Yeah. I mean, for competition from each other in particular.
Yeah.
And of course, the early prototypes were living in a different environment.
Yeah.
They were living in a completely different environment.
Right.
So we don't know how we could possibly have assembled that first working mechanism out of the chemicals that we know about existing naturally,
Right.
abiotically.
Okay. Right. Okay. So there are bricks floating out in the universe, but we're a long way from the cathedral,
We're
right?
very long way from the first cathedral.
Yeah.
Right. Because of course, what do we have? We have now complexes of cathedrals. We have
Mhm.
complexes of trillions of cathedrals.
Right.
That would be you and me.
Yeah. Right.
Right. And every individual cell, a cathedral is as wonderful as they are, is a fairly meager image for the workings of a single cell.
Damn.
Wow.
So, yeah, we don't know how it got started. We just don't know how it got started. And if we find other life like on Mars or something, and it has like DNA, like it has those chemicals.
Right.
It's using adenine, thymine, guanine, and cytosine to, like bound to a, phosphate backbone. Like
We'd be tearing our hair out.
that. Well, I mean, that would mean like it would have to be related to us.
Uh-huh.
I mean, like the idea that somehow abiotically you would come up with exactly that complicated, you know, system of information transfer for cells. I mean, what does DNA need, you know, to be, to make something that closely mimics DNA? All you need are two strips and two different pairs of things that can hydrogen bond to each other.
Mm-hmm.
I could sit down with a pencil and paper and come up with 100 of those in a
Mhm.
weekend
Yep.
that would be somewhat plausible.
Yep.
Other alternative information carrying. I mean, if all we're doing is ACTG, like, okay, it's a base 4 system. Which base is it? Right?
Mhm.
It's pretty easy information coding system.
Right.
I could come up with a better one. I could come up with a 6 base system.
Yep.
And if we find life that's making proteins using DNA and RNA and, the things that every single living cell on Earth does,
Today.
yeah, it would mean, I would take it as prima facie evidence that it would be like it's descended from the same ancestor. Somehow it got both places.
You're right.
And if
Right.
that's what we're looking for, then we're going to miss things that are not that. So
Do you think there are aliens then?
I have no idea. I mean, if you think about abiogenesis, it seems so spectacularly unlikely. Maybe this is the one planet in the universe out of the number that again requires scientific notation and then going home to lay down afterward to think about how many planets there are that would have. Let's just keep it to the ones that have liquid water. Astronomical, literally astronomical.
So beyond trillions.
Right.
Yeah.
Yeah. You're I don't know if it's sextillions or octillions or vigintillions or whatever it would be, but lots.
And we're just talking about ones with liquid water.
Yeah, vigintillions is probably a lot, but
quintillions is not enough.
Quintillions is probably not enough.
Which is water.
Oh my God.
Wow.
But in 15 billion years, that's how old the universe is, and if the stuff coming from the James Webb doesn't completely upset that, which it may. But assuming those parameters, maybe this is the one time it happened. Maybe it's just that unlikely.
Okay. The mathematical odds you need to the number of dice rolls you need to get to us may actually exceed the sextillions of planets that were out there that had to roll the dice, and that doesn't include the quintillions of planets that never even had to roll the dice.
Right. Yeah.
God almighty.
Yeah.
Insane.
Yeah. We just don't know. I mean, people want to pretend that they know more than they do. People, it's just inevitable.
Right. Well, that's, people build their entire dating, their dating life around that. What was that book? The Game, just like swagger in, act like you're a guy with some answers. And it's like, and that people will find that attractive. That's, yeah. Oh, yeah.
Oh, yeah. Well, I suppose I could experiment with that sometime.
Right.
Well, I don't know if that's still on the course, but Dr. Zepeto is doing our 402 science.
Okay.
He was talking about how many stars they think there are.
Yeah.
And they took a picture with the Hubble telescope of what they thought was the darkest spot in the sky. And they found 2,000 galaxies in that one.
That's right. Yeah, the Hubble Deep Field.
Yeah.
Yeah.
Yeah. And then extrapolating upon that, how many are in a galaxy, how many we don't see.
Yeah.
Even ones we do see.
Guessing that that's about the density of galaxies.
Yeah.
Right. Which is an assumption.
Yeah. Yeah, exactly. Yeah.
That there's more stars than sands on the seashore in the earth.
Right. More than likely. Yeah. It's something ridiculous like that. Yeah.
Wow.
I mean, there's got to be an upper limit somewhere because a number that gets thrown around by people who like to be smart and throw around large numbers is, I think, like the number of like protons and neutrons, i.e., the number of baryons in the visible universe, is something on the order of only like 10 to the 80 something. So not even a Google of them.
Mm,
Haha, that's what Google used to mean.
right, right, right. Which is what, 10 to the 100?
Yeah,
Okay.
yeah, it would be 10 to 100.
Yeah.
And then a Googleplex would be a 10 to the Google.
A Googleplex would be 10 to the Google.
Yes.
Whoa.
Yes. Talk about needless numbers. I
Yeah.
mean, like that might even beat Archimedes' sand reckoner, which is, famous for like you would never need a number system that goes that high
Hmm.
ever, except, for yeah. You could daydream up a purpose for it, but yeah, so the number of stars has to be, several orders of magnitude lower than that, but it's still pretty large.
Yeah.
Still pretty large. They don't all have planets, probably. And of course, they don't all have ones. I mean, liquid water is probably an overly restrictive constraint. I don't know for certain that that's the only way you could do it. You probably want a liquid. You probably want a liquid in order for chemical reactions to happen in a loose but confined environment. Gas is too loosey goosey, and solids are too restrictive. Liquids are probably the sweet spot. There are other liquids. I mean, even if you want one that does hydrogen bonding like water, you can have liquid ammonia. There's a lot of ammonia in our solar system.
Hmm.
We don't happen to have a solid planet with liquid ammonia on its surface, but seems any reason why that couldn't happen.
Hmm.
We've got a solid planet with liquid methane on its surface.
Mm-hmm.
Titan,
Right.
if you call it. Yeah, I mean, it's big and round, orbits Saturn, so it's a moon, but
It's planet-esque.
it's planet-esque, yeah, for this purpose is close enough.
Uh-huh.
I mean, if we could send a mission, like a serious mission to Titan, um, and study it for a long time, I mean, and we're really careful about being open-minded about what we're looking for.
Hmm. Well,
If abiogenesis is not stupidly impossible, there might be some very alien form of life on Titan.
but that's kind of our problem, right? Is that we're kind of looking for ourselves,
Yeah.
right? Like the search for life is a little bit navel gazing. Like, yeah, we can say we're looking for life, but in a certain way, we're looking for what we think of as life, which
Right.
may not be
Which has all of these,
Very
amino
specifics.
acids, because those are what life as we know it uses proteins to build all its structures.
Mhm.
There's how many other classes of organic compounds that could be used to build cell structures?
Mhm.
Lots. I mean, you need two things that can bond together.
Mhm.
Well, you can make esters by, bonding an acid and an alcohol group.
Mhm.
You can make, other nitrogen bearing bonds. You can make other oxygen involved bonds. Or you could just have really long floppy hydrocarbons.
Mhm.
Why would that be impossible?
Mm.
Why would some other alien sort of machinery not be able to fab up, just really long hydrocarbons and use those molecules and then, put little functional groups on the ends of them?
Mhm.
We don't know.
Yeah.
And until we, find something else, we won't really know. We won't have any guess as to how big the parameter space is.
Right.
Again, like you said, navel gazing. We'll go back to, well, this is what we have. This is the one example we know about.
Right. Right.
So,
Right. Right. Wouldn't that be ironic? We searched the entire visible universe, and the whole time we were just sort of looking at our own navel. You know what I mean?
Yeah.
in a sense, yeah.
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 Yeah. What's your you've taught at a Catholic college. I'm sure you've met and interacted with students who would describe themselves as creationists. And yet even in our own even in our own conversation, you've brought up evolution. What's your take on evolution?
So there's two different aspects of it. So
Mm.
there's the one aspect that you could call the succession of species.
Mm.
So again, coming at it from a geological perspective,
Mm.
there's been history. The earth has done things.
Mm-hmm.
Unless God has done some really ridiculous, put up job the Earth has been around for a very long time,
Hmm.
and it has had a sequence of different living things over the course of that history.
Mhm.
Sure. So that's what I mean by sequence of species.
Hmm.
There's been a succession of species.
Hmm.
There has been a succession of species over hundreds of millions of years.
Okay.
That that I think you have to be really ignorant or really sort of like be lying and having an agenda to deny.
Okay.
Now, how did that succession of species come into being?
Hmm.
So there's the neo-Darwinian orthodoxy of like, well, it's, mutation creates this variety and then natural selection selects over the variety. Now, natural selection is also too obvious to be denied.
Hmm.
Things that don't keep up die. There's a competition.
Okay. So the competition aspect is obvious, and therefore the selection aspect is undeniable, right?
Yeah. So the question is, how
Agreed.
does that get grist to select over?
Hmm.
And that's where the people like Michael Behe come in, the intelligent design people. So like, Chesterton, I think, has a saying, the reformer is usually right about what is wrong, but he's almost always wrong about what is right. So they have a problem. They have correctly identified, I think, a problem that just random mutation and selection over that random mutation won't get the job done.
Hmm.
It won't build new functionality. Point mutations in the genome just won't do that.
Because it's not innovative enough. I think I
It
remember
won't,
reading
you have to
that
do too
somewhere.
many steps at once.
Mhm.
You just have to probabilistically have too many coincidences happen at once, even over geologic time.
Mhm.
And there have been way too many species come into existence and way too many new functions, added to living things library over that course of time,
Okay.
for that to be the mechanism. So the problem is of course, that, somebody like Behe has no, like, he just says, well, that means it was designed.
He's the author of Darwin's Black Box. Is that right?
Darwin's Black Box and also Darwin Devolves, which is a horrible thing to read because in Darwin's Black Box, he's an actual intellectual. He's engaging. He's got some ideas. He's not perfect. No one is. In Darwin Devolves, he's become a bitter old man who's like, actually, not only was I right, I was so right, and everybody else is an idiot. There are people who, there are scholars who are like that in their old age that are horrifying to encounter. Horrifying.
You're like, you got through a little devolving yourself there.
He has, yeah, that's arguably the case. That's arguably the case. So, but yeah, but that problem that, the problem that the intelligent design crowd has is that they almost, well, I mean, Behe, I've only read Behe,
Hmm.
to speak of, a little bit of other people, but mostly just Behe.
Mhm.
And Behe just will like, it's like he goes from being a scientist to being engaged in debate where he's going to score points by not opening himself up to criticism,
Mhm.
which is not science.
Right.
Science is speculation, admission that it's speculation, openness to testing, you know. Okay, so how does this intelligent design get instantiated in human beings?
Hmm.
I mean, I am all for the fact that we should recognize that there is such a thing as final causality.
Hmm.
Cool. Not
Yeah.
denying that.
Mhm.
There's all four forms of Aristotle's causality, but I want to know how it efficiently got done.
Right.
It's always there.
Mhm.
It's worth asking. And he will not go there. He will not give himself the slightest opening there. So he won't propose anything to get criticized.
Right. Right.
So the question is, you know, the reality is you point at it and say, okay, you have basically in a Popperian sense, you've falsified random mutation and natural selection. Now you haven't falsified natural selection, that definitely happens.
Hmm.
But you falsified the idea that random mutation in the way that it's been canonically, taught in the 20th century, would be able to create the variations that natural selection needs to select over.
Mhm.
That can't happen. So that means there's some other mechanism.
Uh-huh.
And so the question is then to go find it,
Uh-huh.
go find evidence of it. So
Uh-huh.
apparently changes can happen together,
Hmm.
in a chorus, as it were, And living things apparently have this mysterious ability to do them in surprisingly helpful ways.
Okay.
So there's almost been a sort of meta evolution in a sense where like living things are designed to change and designed to change in helpful ways. Because they change in helpful ways far too often for random chance to explain. And so
we're optimizing a lot faster than random mutation could provide the grist for.
Right. Yeah. And so there is some evidence that people have begun to amass over the past few decades of sort of spontaneous genetic engineering, so to speak. The living cells, especially when they're under duress, will actually start, actively changing their own genome in strange ways. Where that's going to lead,
and we don't know where it's coded for that to do that, right? Like,
yeah, I mean, is it even coding in the conventional sense? Is it some other aspect of the way that living beings are structured?
Right. That there's a sort of invisible consciousness or something.
Well, I mean, it would probably be instantiated in some other chemical aspect other than just the DNA.
Oh, okay.
Something else that's being carried along from cell to cell that we haven't exactly paid due attention to.
Right.
Would that be linked to something like gene expression, which is
yeah, turning on and off genes would definitely be part of that, right? So, and some of those genes, will express or not express things that then either keep the genome intact or open it up to changes. I mean, it's such a complicated system. Wheels within wheels within wheels.
And when you say succession, you said succession of species. Am I?
Yeah.
Okay. So that's what some people might also say, like common ancestry, right?
Well, so that's different, right?
Oh, okay.
So a succession of species simply says there have been different species over Earth's history. That's
Ah.
not saying that they have a common ancestry. That's
Ah.
just saying there's been changeover.
Okay.
Now, the argument for common ancestry is that we have an insanely complex system of information tracking, protein synthesis, whole bunch, this, that, and the other thing in a partridge and a pear tree
Yep.
that we share with every last living cell that we know of. Every last one. We all use ADP, ATP to handle energy. Like we just all do that. We all use glucose for energy. I mean, and then there can be a million variations on that theme, but they all do that. They all do that.
ADP is the MVP year after year. Yeah.
Right. Exactly. I mean, I guess it does the body good.
Right.
But so there are just too many chemical similarities of how we do business to not have basically, some, one ring to rule them all.
Okay. To think that, the reptiles arrived at it this way and we've arrived at the exact same spot through an entirely different path. That's sort of
it just looks too,
that looks like a stupid conclusion.
That would look like, alien genetic engineers, right? Or, God, literally, getting his fingers dirty and like, changing things, far beyond the capacity of ordinary chemistry to accidentally come out the same way.
Right.
On this, insanely detailed master plan.
Do you have any opinion or even speculation? You're on a podcast, not a scientific board, but on how consciousness arose in primates?
Good heavens. Yeah. So I will be a little heterodox in that I wonder if there is in like maybe not even just primates, but mammals in general, maybe even further back in the, vertebrate lineage of something, gradually approaching consciousness.
In vertebrates.
Yeah.
Not mammals necessarily, like earlier than that.
Yeah, earlier than that. Yeah. Yeah. I mean, it's just speculation.
Okay.
If I sat down to study that, if I sat down to make that my life's work, I would lay out all these possibilities and say, have we investigated those?
Right.
I think
Right.
there
You can't say definitely not.
say definitely not. No. And of course, how you would investigate it, that would be a very tricky question. But there would be, I mean, there's some biological precursors to consciousness, would be my suspicion. I mean, they're the people who Simon Conway Morris is one of the biggest names in this, who talk about convergent evolution. And so if I look at it through that lens, like somehow the universe was designed to allow the existence of life as we know it. And once life as we know it got started, it was going to move in the direction of sentience. And that would include all these, various precursors to consciousness, however that works. I mean, there's a physicist named Roger Penrose, who, now that Stephen Hawking is dead, is, I think, about undisputably the reputed to be the most intelligent physicist alive. He has some very strange ideas about mind and consciousness, and that there's, that he thinks he's identified some candidate, structures within cells that might have such different physics that, that could somehow be related to consciousness.
Right.
One of those books on my shelf that never quite gets read. But I read his Road to Reality. I mean, and by read, I mean I've looked at all the pages.
Right.
And there's the mathematics that I don't follow, and the physics that depends on that mathematics that I therefore also don't follow. Which is frustrating, because I don't think it's because I couldn't follow, but it's because my training went in a very different direction.
Right. Right. How much bandwidth do any of us have?
Unfortunately. But yeah, so as far as that goes, yeah, I suspect that cats and dogs and dolphins and definitely chimpanzees and orangutans probably have a lot of the cellular mechanism that supports consciousness. And it was a final few things that got thrown into place for us to become what we are from a physical perspective.
Right.
And
We haven't quite nailed down what those final few things are. We know they must be
oh
there.
heavens, no, I don't think we're all that close.
Right.
I mean, that's, in case you can't tell, my money is always on. It's not going to happen that soon. It's not going to happen that fast. It's not going to be that dramatic. It's not going to be that clear. Nevertheless, the game is worth playing.
Right. I mean, your model is more like we need to see progress as the coming in of the tide, not as the tsunami. Right. And people are constantly calling in the tsunami. Right. This changes everything.
That's
you know
right,
what I mean?
yeah. I
The
mean,
generation raised on reality TV.
Right.
Right. There's always some character ready to scream at the camera. This changes everything.
Right. Exactly.
Yeah.
Yeah. Until we're all basically numb to it.
Right.
I mean, that's our, and your, venture capital people are always looking for the next quote disruptive thing, because it will, in the course of destroying a whole bunch of other stuff, you'll make a lot of money.
Right.
Or at least that's the hope.
Right.
I don't know how often, that comes out that you destroy a bunch of stuff and don't make money, but I have to imagine it happens sometimes.
Yeah. No, I think it's true. I do think that, we know about our superstars, our tech superstars, but I mean, how many people have worked 80 hours a week on a reasonably good idea, and no one knows them, the project went bankrupt, and then they became consultants at some other firm, and they might still be fine, but they're not Bill Gates, right? They're not Zuck, whatever.
Exactly. It's only so much space for those guys anyway.
Right. There's only so many mountaintops.
Yeah.
Well, Dr. Giesting, we could be here all night chatting, and I really do hope that you'll find time to return to Lander and return to the Fireside for another chat.
Oh, absolutely.
But I'm sure we have to wrap up this episode. But it's been a delight. I mean, it's my head is swimming, but I think on the other side of the laps in this pool, I'll emerge just a little bit smarter, a little bit. So, but yeah, it's been a real pleasure having you on, and we'll definitely mark this down as one of our most fun episodes.
Oh yeah. This was great. This was a very fun evening. Thank you for inviting me.
Of course.
Thank you again. Yeah.
All right.